This conference. First speaker is Riccardo Montalto from the University of Milan. He tells about quasi-periodic study variant structures in incompressible fluids.
Okay, so first of all, let me thank the organizers for, for this invitation. So the content of the talk is essentially about the 2D Euler equation and a little bit some dynamical properties of the 2D Euler equation, in particular around shear flows. So let me start with a little bit with an introduction. So I consider the 2D Euler equation, which is very well known. So the unknowns, it is an equation for the velocity field for an incompressible fluid, and the unknowns of the equations are, so we are in 2D, so we consider the equation in a domain, in a subdomain of R2, and the unknowns are the velocity field, which is b-dimensional, which is a b-dimensional vector field, and the pressure. So when you write it in the vorticity formulation, so the vorticity is actually a scalar in 2D, and it is the curl of the velocity field. One essentially has a transport equation, dTv plus u dot nabla v equals 0, and you can reconstruct the velocity field in terms of the vorticity by taking the symplectic gradient of the inverse of the Laplacian of the vorticity. And the symplectic gradient is actually, if the variables are x and y, it is dy minus dx. So let me summarize a little bit somehow some recent and classical results, and most of them are exactly in 2D. So of course, the local existence for the equation is well established. One can refer, for instance, to the papers of Cato in the 70s, and it is made by vanishing viscosity methods. Then actually in 2D you have one has global existence for smooth solutions, and the key point is that actually since it is essentially a transport equation, the vorticity is preserved, is preserved. The L infinity norm of the vorticity is essentially a constant of motion. Okay, so when you consider the fluid particle and you let and you compute the vorticity on the particle trajectory, you have that it is essentially uniformly bounded in time, and this allows to prove the global existence of smooth solutions. And one has also for Sobolev norms for S large enough a double exponential growth. So this is a classical result by Belkato-Maida. Actually, also for weak solutions, one has global existence, which is actually suggested really by these estimate, because the L infinity norm is actually uniformly bounded in time, and indeed, well, at least if one considers omega bounded, one has that there exist global weak solutions for the Euler equation in L infinity, if the initial datum is in L infinity. Okay, then also one can ask if this bound is optimal, and okay, on domains without boundary, I think is open, but at least on the disk, there is actually a paper by Kiselev and Sverak which tells you that you can construct a velocity field for which you have double exponential. Then also another interesting point is that, okay, the energy estimates essentially works in a regularity which is dimension over 2 plus 1. And also, in some sense, this is optimal, because if you consider this borderline regularity, the problem is imposed. And this is a beautiful result by Bourgain and Lee. Imposed in the sense that if you take, okay, close initial data, then you have fast solutions at some time. Okay, so it's really imposed. And then there are some very nice, very beautiful results, recent beautiful results, which tells you that if you put a forcing, okay, if you put a forcing, you have no uniqueness actually. So there is the result of Vichy for Euler, and then the more recent results for Navier-Stokes by Abritton, Brouet, and Colombo. Then what is more the goal of this talk? Questo però è. Taglia. Vabbè.
No, Madonna.
Okay.
I'm not a YouTuber.
No, okay. So what is more the goal of this talk is actually to investigate the okay, for the 2D Euler, the asymptotic behavior of the solutions. Okay, this I copied essentially from the talk of Michele of the last week, and it is because it is fancy. And there is actually a conjecture of Zverak which tells you that generically you converge to something compact, so to a steady state or to a recurrent solution for t which goes to infinity. And actually, what I'm interested in is actually the dynamics around okay, shear flows. What is a shear flow? So first of all, let me consider omega, which is a channel. So it is x is in r, y is in -1, 1. And then a shear flow is a velocity field of the form alpha y 0. So it is, of course, the solution of the Euler equation. It is divergence free, and okay, it solves the Euler equation. And actually, in particular, I'm interested in the simplest shear flow, which is the Couette flow. So the first component is y, the second component is 0. So essentially, it is like a velocity field. So the fluid particle stays on layers for all times. So you have layers, and then any fluid particle stays on the same layer for all time. So what is, I mean, so the investigation around Couette flow started very early in 1907 at a linear level. So you consider the Couette flow and you linearize around Couette flow. So you have like a transport equation of this form in vorticity, so dtv plus y dxv equals 0. So this is a transport equation and you can solve it. And there is actually a strange phenomena. So of course the Euler equation is a reversible equation. So it's time reversal. But you have some dissipative phenomena, actually, which is a bit strange. Because it's not dissipative equation. So what you have is the following: it's the phenomenon of the implicit damping. So here you can make it by hands because the solution is explicit. And what happens is that okay, asymptotically. So if you take the solution, then the second component of the velocity field tends to 0 as t, which as t goes to infinity. So what does it mean? It means that asymptotically you come back to a shear flow. So essentially, at least at the linear level, shear flows are like attractors for the dynamics. And okay, of course, at the non-linear level is okay, much more complicated, but there is okay, starting from 2015, it was proved even the nonlinear implicit damping. And here I want to give an informal statement of what it is. So essentially, I think Masmoudi and Bedrosian proved it for the case in which you have t times r. And then there was an extension by Ionescu Gia, indicate when you have x in t and y in -1, 1. So the informal statement is the following. So take an initial datum, which is close to Couette. Okay, in X, where X is essentially Gevrey. Gevrey means something between infinity and analytic. But you can think analytic. Then take the solution of the nonlinear of the Euler equation, so the nonlinear equation, and then you have that asymptotically you converge to you come back to a shear flow of the form alpha infinity of y 0, where alpha infinity is something which is close to the Couette flow. Okay, so this is the nonlinear implicit damping. And actually here there is a problem, okay, in the following sense. So, okay, this theorem tells you that if you are somehow regular enough, there is shear flows are attractors. But then, what happens is that in the experiments, you observe something different. you observe that there is a transition from the shear flow to something else, and this something else is the formation of like periodic patterns or invariant structure. So somehow the experiment suggests that you have a different phenomenon. Okay, so what is the problem? The problem is the regularity. So if you are regular enough, then you have attractors, but if you are irregularity, you have the formation of these patterns, so you don't have convergence to shear flows again. And then I want to show you, I think it is the next slide. So you see that, okay, here you start from a shear flow, and then you have the formation of these periodic patterns, or anyway, or you can also call invariant structure, and this is the so-called Kelvin-Helmholtz instability. And then also here you can see that, okay, this is a viscous fluids. So if you let the viscosity become smaller and smaller, then you have the formation of this invariant structure more and more. So it's essentially when you approach to an inviscid fluid, you have this phenomenon. Okay. And let me just summarize a little bit the literature on the inviscid damping. So essentially, okay, this is a phenomenon that was investigated by Villani for plasma physics. And then, okay, at the linear level, of course, the first computation was made by Kelvin Orr. And you can find a clever proof in Lin and Zheng, which is a recent paper that I will talk about later. Then at the nonlinear level, the first pioneering paper was made by Bedrosian and Masmoudi. Then there is an extension by Deng and Masmoudi, and then Ionescu Gia. And then also Roberta and Michele worked on this phenomenon for stratified fluids, and it's quite recent. There are two papers, one linear and one nonlinear. And also there are some papers. There is a paper on compressible fluids by Antonelli, Dolce and Marcati. And then there are several papers for, let's say, more general shear flows, in which inviscid damping is investigated at the linear level, okay, by Zillinger, essentially. Okay, on the other end, okay, what about the formation of invariant structure in fluid mechanics? So I just want to mention some results for equations in fluids. So the investigation is essentially about the bifurcation from vortex patches. So vortex patches are like, okay, you take an initial datum, which is a characteristic function of some domain with smooth boundary, and you let it evolve. And then there are several recent results on the bifurcation of multi-periodic waves from vortex patches, which I list here. Then there are some results for Euler and Navier-Stokes equation, where you put like a periodic or multi-periodic forcing. Then there are also other kinds of proofs which are not by KM methods or normal form methods, by Cruzeil-Farou and Ciso-Peralta and Lisaur. And then, let's say, more related to this talk, I want to discuss a little bit more these kinds of results. So, essentially, there is, first of all, these results by Lin and Zheng, which is the following. So, take the Couette flow, and then you construct like a periodic traveling wave, which is close to the Couette flow. And here I will discuss a little bit later in details the issue of the regularity threshold, which is important. Then another more recent paper is by Michele with Tarek and Klaus. So okay, here also very interesting because they considered actually the Kolmogorov flow, which is like something different from the Couette flow, because the Couette flow is increasing, is strictly increasing, and Kolmogorov flow is oscillating. And what they did is essentially they prove that there is essentially never implicit damping, so around wet flow. So they constructed actually at any level of regularity, steady states or traveling waves and traveling waves. So they constructed steady states, but as a consequence, you can construct biperiodic waves from their theory. So there is never implicit damping around Kolmogorov flow, which is sinus of y 0, and so they did it for any Sobolev index essentially. So there is never implicit damping around Kolmogorov flow. And then what I want to discuss in this talk is this paper that I did with Luca, Franzoia, and Nader Mahmoudi, in which we constructed actually multi-periodic traveling waves bifurcating from the wet flow. And so let me just give a little bit of setup. So, I consider the equation in the channel, and of course there is, I put boundary conditions at -1 and 1, which tells you that the fluids cannot flow out from the boundary of the channel. So this is the impermeability condition. I put the velocity field at -1 and 1 equals 0. Okay, then what I want to do is the following. So is to construct. So the first thing is to construct space quasi-periodic steady states. So you have two variables, x and y. I want to construct quasi-periodic steady states with respect to the variable x. So you have the variable y, which is the direction of which gives essentially the direction of the shear flow. And then what I want to do is to construct is to have quasi-periodicity in the transverse variable, which is x. Okay. So what does it mean? It means that I want to construct a time-independent solution, so steady states, which have the following formula. So this is essentially the definition of quasi-periodic function. So it is a function of u of xy of the form capital U of omega xy, where capital U is it depends on, let's say, k0 variables, and k0 is the number of the frequencies. So it's essentially an extension of periodic function. So when you have more frequencies, more than one frequency, and the frequency omega is irrational, which means the following. It means that you don't have resonances with the integral vectors. So omega dot L is different from 0 for any L which is different from 0. And actually, under this assumption, if you consider, you have essentially the simplest version of the ergodic theorem, which tells you that if you consider this flow on the k0 dimensional torus, then you fill densely the k0 dimensional torus. So it is essentially a linear flow, and you have that the orbit is dense. Okay. And actually, this seems a bit artificial, but as a consequence, very easy consequence, you can have that if you do this, you construct traveling waves which are quasi-periodic. Okay, it's quite easy. At least some particular traveling waves, which are actually quasi-periodic both in space and time. It means that essentially the wave number is collinear with the velocity of the wave. And then I will discuss more in detail this ability, because I wrote the formula. Okay, then let's see how to construct actually steady states of the earlier equation. So in vorticity, Michele, please. Yes, sure.
I remember, so you're taking x in R, and then
X in R
in the equation, in the other equation, right? X is in R. And then here it is. So you're constructing something with x in R, or?
Yes, because essentially, then x is in R, but then this variable is on the torus.
Yes.
Because you have to consider like that these are clear lines, and then they are like that.
Okay.
So if you think that the bidimensional picture is more or less like. So essentially, in the end, the equation that you have to solve is an equation for the embedding. Okay. Not for really for you. So it's so the problem becomes periodic in this variable. That's but x, okay, small x is enough. Okay. But essentially you have to have, okay. So you have to consider this variable modulo value. That's and okay, so okay, let's see. Okay, also this is quite standard. So if you want to construct the steady states, it means that you take the Euler equation and essentially time derivative disappears. So the equation for the steady states in vorticity appears like that. And then it is convenient to consider the equation for the stream function. Actually, the stream function is actually it is connected to the velocity field by taking simply its symplectic gradient, and also it is connected to the vorticity by solving a Laplace equation. So if I give you the vorticity, the stream function is determined somehow up to harmonic functions by solving the Laplace equation, Laplacian of C equal to V, where the Laplacian is the bidimensional Laplacian. So if you write the equation in vorticity, if you write this equation somehow in the stream function formulation, then you have something of this form. So you have essentially that the equation becomes Poisson bracket between the stream function and the vorticity equals 0. And Poisson bracket is, okay, what you find in a Hamiltonian system. So you have two functions, and then the Poisson bracket is dx psi dyv minus dy psi dxv. So it's really what you get in a Hamiltonian system. And actually, also another, okay, a very easy property of Poisson brackets is the following. So if you have a function, so if you have psi and you have a smooth function of psi, and you make the Poisson bracket, then it is 0. It's an easy computation. Then, okay, what is the summary of this is that if you solve a Laplace, if you find the nonlinearity f, and if you solve a Laplace equation, Laplacian of psi equal to f of psi, then essentially you have solutions of the steady Euler. So in the end, you started from here and you transformed it in an elliptic problem. That's a little bit okay. But okay, so the difficulty actually in these kinds of things is that actually it is like an inverse problem because the nonlinearity is unknown. So it is not given. You have to construct the nonlinearity in such a way to have a solution which bifurcates from the quet flow. So f and psi are somehow the unknowns of the problem. Okay, and then indeed I want to explain first how to do it in the periodic case that is much simpler. So first of all, let me give okay, an informal statement before then introducing like 100 parameters of the theorem. So okay, as I said, the goal is to determine a quasi-periodic function which solves the steady Euler. So the unknown is actually the stream function. And the theorem essentially can be stated at least informally as follows. So give me, okay, the number of frequencies, give me a small parameter, then I find a family of stationary solutions, which are quasi-periodic in X. Of course, for some frequency vector omega in RK0. And this family is close to quet flow, in the following sense. So it is close to the quet flow in this space. So the space is hs in time, h7/2 minus in y. And this is actually essentially the optimal threshold that, it is the threshold that also in the periodic setup you have. So you have this regularity. So if the regularity is lower than 7/2, then you can do the theorem. You are close to the quiet flow. But if not, you are far away from the quiet flow. Okay, so this is the threshold that we get. So we are in low regularity. But we can have actually in the variable x, the regularities are very high. Okay, so that's a little bit the informal statement. So you have an estimate for the difference of the solution from the quiet flow in this regularity.
So maybe it's stupid. What do you mean by bifurcate?
Simply close. So there exists a solution psi epsilon such that the norm of psi epsilon minus y square over 2 is smaller than epsilon. Yeah, it's sorry, it's dynamical system terminology somehow. Okay, but yeah, it's simply close. Okay, and then this is also, maybe I didn't comment it. So if you have the quiet flow y0, the stream function can be computed easily, and it is y squared over 2. It's simply because it solves psi prime equal to u equal to y, and then u. So this is the only somehow symmetric solution of the Laplace equation for the stream function of the quiet flow. Okay, and as I said before, the consequence concept for the traveling waves is the following. So essentially, this theorem implies that you can have quasi-periodic traveling waves of the following form. So you have, okay, give me C, and then the traveling waves has the following form: is Cy plus the steady state computed at omega times x minus ct y. And so what does it mean? It means that essentially the wave number is collinear with the velocity. So the wave number is omega, and the velocity is omega times c. So it's right. So the wave number is here omega, and the velocity is c times omega. So it's so they are collinear. So they are not. I mean, it is not the most generic traveling wave, but it's kind of traveling wave. Okay, then let me comment a bit on the regularity. So okay, actually. Of course, okay, the theorem works only in low regularity, which became 3 alpha, because here I stated on the vorticity. So if you have 7/2 on the stream function, you have 3 alpha on the vorticity. You have 2 derivative less. Okay, but then, okay, of course, the problem of the nonlinear implicit damping in HS, I think it's still quite open. So yeah, the theorem that I stated at the very beginning says that if you are close to quite Ingevre, then you have implicit damping, but then there is a gap between H3 alpha and Ingevre. So it's but it is an hint that you should have implicit damping. And then, okay, of course, this is actually a counter example to check. Okay, the theorem tells you that you cannot have implicit damping when you are in low regularity because you have invariant structure, and then you don't dump down to the A2 shear flow. So you have oscillations. You have oscillations at infinity, and then you don't have enough structure. Okay, so. Okay, maybe I want to just comment. Okay, I want to how much time? So okay, perfect. So what I want to do now is to a little bit to describe the periodic case. Okay, so how Lin and Zheng did in the case of periodic traveling waves. Okay, so okay, the statement is actually the following. So give me a period, and you are in low regularity. Then they constructed the nonlinearity, so which is an unknown of the problem, as I mentioned before, and the stream function, which is a t-periodic in a transverse variable, which solves this Laplace equation, and the vorticity of the stream function is close to the vorticity of the wet flow in HS. And actually, this is a non-trivial solution in the sense that this is not a shear flow. And then another beautiful thing is that they proved that if the regularity is high, if you are in high regularity and the threshold is exactly 3/2, then you have a rigidity argument, which means that assume that you have a traveling wave which is close to wet in HS for S large enough. Then this traveling wave has to be necessarily a shear flow. So it is like a rigidity. So in this sense, what I was telling before about the optimality of the result. So this is something that suggests you that the result is optimal, because then if S is large, you cannot have traveling waves. But this does not mean that you don't have implicit damping, that you have implicit damping. So still, so this is like a rigidity argument, and also in the paper of Michele, it is done. So there are there are some rigidity arguments when the torus is an irrational torus, right? I mean, it's rectangular torus. So if it is rectangular, you have close to Kolmogorov, then you have something like this, right? Okay. Okay. And actually, okay, maybe you can, okay, you can also, maybe just a small thing, you can also optimize these in the sense, you can do maybe better in the sense that you can distinguish the regularity in X and Y. So the important thing is really that in Y you cannot be more than 3 halves, but in X you can be as regular as you want. So if you go through their proof, you can see that really you need an embedding in Y, not in X. Okay, and then what is the point? So how they did? They did as follows. So first of all, you have to construct it. Okay, then how they did? So take a perturbation of the wet flow, okay, which is something which is small with gamma, and they really choose the thing, and now I tell you why they choose this thing, but the choice is not unique. I mean, so they need these to have something that I tell you later. So essentially, okay, psi gamma. So U gamma has to be a steady solution. So it means that as any nonlinearity that you construct, it has to psi gamma has to satisfy an equation like that. Okay. Okay. Then what you need? So you want to construct something which is periodic in X, but then you have to solve a Laplace equation. So that's a bit of a problem. So when you have oscillations in Laplace equation, when you have negative eigenvalues, and this is exactly what you need. So you need negative eigenvalues at least at linearized level. So take the Laplace equation, linearize around psi gamma. This is the method of, anyway, by the way, it is called spatial dynamics, in the sense that when you have an equation of two variables, you consider essentially one variable as time and the other as space. So when you have a Laplace equation and you have like a negative eigenvalue, then it is like a wave equation. No, it's not elliptic, at least in that direction. So, and the point is that the way in which you want to find f is to have that this operator has a negative eigenvalue. That's the purpose.
Can I answer the question? So when you do this, how do you deal with initial versus boundary conditions? So if you think of this as a wave type equation, what are the initial conditions?
Well, no, it is not a Cauchy problem. It is like a bifurcation problem. So, okay, so essentially the purpose is to find f in such a way that the linearization around this shear flow has a negative eigenvalue. And, okay, only one negative eigenvalue is very easy because you study in elementary courses of quantum mechanics, the potential that you have to choose is the Dirac delta. It's like if you have a Schrödinger operator, which is dy square minus dy square minus Dirac delta, then you have like, okay, the spectrum is positive, and then there is a negative eigenvalue, only one negative eigenvalue. It is essentially elementary quantum mechanics. The point is that this is, okay, if you do it directly this is not smooth. Then you have a little bit to regularize, and the way in which they regularized is exactly by means of this error function. But it's not the only way. I mean, it's not the only way. Okay, it's not unique, but it works. So essentially,
the amazing thing is that it gives the optimal result.
Huh?
The amazing thing is that it gives
the amazing. Yes, it's really no, indeed. It's essentially, well, it's also what happened to, I mean, we tried, and it's okay. Of course, the point for multi-periodic waves is to have a Schrödinger operator with, well, not only one negative eigenvalues, but an arbitrary number of negative eigenvalues. So it's okay. But anyway, it's really, I agree that it's really astonishing that they find it. So, and then if you do this choice, essentially the potential of the Schrödinger operator, which is connected to the shear flow where you start. So you started actually from the shear flow. And the formula for the potential is the quotient between the second derivative of the shear flow and the shear flow. And actually, this is close to Dirac delta, to minus Dirac delta. And then you can prove, like, by perturbative arguments, like a theorem which tells you that there is one negative eigenvalues and the rest of the spectrum is positive. Okay, this is not so difficult. This is not so difficult. So, of course, okay, the boundary conditions that you take the Dirichlet boundary conditions, which follows from the impermeability conditions somehow. So it's, you consider this operator with the Dirichlet boundary condition, and you prove this theorem on the spectrum. So, and then as a consequence of this, you find actually steady states which are oscillating in X. So the steady states bifurcates from these negative eigenvalues, essentially. So if you consider the negative eigenvalues, which I called minus k0 square, and take the eigenfunction, phi 0, so what you have is oscillations of this form. So on the velocity field, you have, okay, the shear flow. Then you have, epsilon phi 0 prime cosinus of 2 pi over t epsilon x, and then for the second component of the velocity field, you have epsilon 2 pi over t epsilon phi 0 sinus of 2 pi over t times x, and these are called Kelvin's cat eyes. And there is a nice picture from Maida Bertozzi. I mean, it's something if you study the level sets of the stream function, you have something like that. So how is the proof? The proof is the following. So essentially, you have that psi gamma has to satisfy something like this, and then now that you have the potential, you have an equation like phi prime composed by psi gamma equal to the potential. Okay, but then what happens? This is essentially an ODE. And how do you solve this ODE? First of all, you have to invert. You have to invert this function. And the fact, the core of the stuff is that since U gamma is monotone, psi gamma is like a parabola, and so by symmetry you can reduce it to positive values of y. And but there is monotone, and then you can invert psi gamma, and you can find essentially an equation for f, which is exactly what I wrote here. So essentially, if you invert psi gamma, then you have an equation for f, which is a Cauchy problem for f. And then Q is given, psi gamma is given, then this you can solve and you find f. So it's like an inverse problem, okay? So you have to determine the nonlinearity having already the solution, at least at unperturbed level. Okay, once, so you construct f, and then in order to construct the perturbation of the shear flow, you solve like a bifurcation problem by means of essentially variance of implicit function theorems. It is the Crandall-Rabinowitz theorem, essentially. So it's the bifurcation from a simple eigenvalue, and you apply it in a really direct way, and you get that essentially this theorem. So, but the core is that to construct f, you use the stream function of the Couette flow that you choose at the beginning, and the potential. That is, the potential is actually recovered by the stream function of the Couette flow, or by the or by the shear flow that you prescribed at the beginning. So the point now is that how to have quasi-periodic oscillations. So well, I said that for periodic oscillations you need one negative eigenvalue, and then you need the Schrödinger operator, which is essentially the one in which the potential is the Dirac delta. But then also here you have intuitions from quantum mechanics. When you have a Schrödinger operator with an arbitrary number of negative eigenvalues, well, when you have the potential well. So the potential well is like this one. So it is like the depth is minus e square, and it is large to r. Okay. And what happens if you study somehow the spectral problem for the Schrödinger operator with this potential is that the number of negative eigenvalue is given by the product between E and R. So essentially you move E and R as parameters. Well, essentially it is one parameter because the relation is E times R constant. And then you play a little bit and you have a finite numbers of negative eigenvalue, which I called K0. Okay, of course, there is the same problem. This is not smooth, but you can have a smooth approximation in some sense of the potential well. So smooth approximation, I mean that outside the singular values, which are essentially R and minus R, you have uniform convergence. So there is actually an explicit formula of this, but I didn't want to write because it is a bit technical, but there is an explicit formula. So it depends on some parameter, M, and if you take M large enough, it approaches to the potential well, in this sense that I tell you before. Okay, then if you study the spectrum of the Schrödinger operator minus d square plus qm, then you have K0 negative eigenvalues. And this suggests you that in the Laplace equation that you get, you have you have oscillations, but not periodic, quasi-periodic, with these frequency vectors. Okay, of course, also this theorem, okay, also this fact you prove in a perturbative way. So you solve essentially explicitly the problem for the potential well, and then you perturb. Okay, so it's essentially the way in which it is done. You need also smoothness because you need even analyticity in the parameter E. Okay. Okay, then the second thing is okay, how to determine. Okay, so here is a bit different in the sense that it is not exactly like Lin and Zheng, let's say the timeline, because I start from the potential. They started from the wet flow, from the shear flow, but here I start from the potential, and from the potential I determine the stream function at the unperturbed level, which has to satisfy like an ODE like this. So if you remember before, the formula of the potential is given by the quotient, by some quotient, and that's exactly what I want to do. So I want to determine the stream function in terms of the potential by solving this ODE. And what you get is the following fact, is that when you are outside the well, you are close to Kuet. But when you are inside the well, you are close to something like Kolmogorov. Okay, when you solve this ODE, you have like an asymptotic behavior more or less like this. So inside the minus RR, you are like Kolmogorov with a fast oscillation. And outside, you are close to Kuet. So somehow the proximity, of course, of the solution to Kuet depends on R. But you take R small enough and E large enough. So it is true that you have oscillations, but it is even true that the interval is small. So if you play in a good way with parameters, you can prove this theorem, which tells you that, okay, this stream function is close to Kuet in H3 like square root of R. If you go into H4, is 1 over square root of R. But then, if you interpolate, you have that you are small with R up to 7 over 2, because you have interpolation. So, okay, also this is optimal.
I mean,
it's
you have to take it slightly below, right? Because
slightly below, yeah.
8, 7 out is exactly order 1.
Slightly below, exactly. 7 over 2 is 1, order 1, but 7 over 2 minus is R to some power. So that's I mean, it's really okay. It's astonishing that this computation works, because it is a choice, but then as you were mentioning before, it's you know, it's but okay, but so it would be even interesting if one see if R is large, then you should approach Kolmogorov, no? But okay. So if you consider R large, it means that the dominant part is Kolmogorov, but then one has to see what happens. Okay, so the first thing that one can observe is that, okay, of course, since you have this behavior, you lose monotonicity. You have a finite number of critical points. Okay, because you are oscillating. I mean, inside minus RR, you are oscillating. Okay, of course, you are monotone outside, but in this interval, you lose monotonicity, and that's a problem to construct the nonlinearity. That I want to. It's the next thing that I want to discuss. So this is essentially a rough picture of psi m. So you have here outside minus R and R, which are these two values. You have like you are essentially the wet flow, and inside you start oscillating, and so you lose monotonicity inside. Well, let's go to the nonlinearity. Okay, so the nonlinear. Okay, the nonlinearity has to be determined in such a way that psi m, which is this shear flow that I found, solves like an equation of psi second equal to f of psi m. Okay, and then of course the point, okay, I want to construct a smooth nonlinearity, so a CS nonlinearity. And what is the difficult part? The difficult part is essentially that you have interval, you have to do it locally. So you have to consider the intervals between two critical points. So between two critical points, you are monotone. So either you are increasing or you are decreasing. Inside here, you solve like a Cauchy problem for the nonlinearity, but then you have to make like something like a partition of unity to glue it together. I mean, but you have to construct it locally, because the only way in which you construct it locally is to use monotonicity. And actually, the strategy is indeed this. So essentially, you take an interval between two critical points, and then you solve you want to solve, okay, the nonlinearity satisfy the relation deep psi fpm of psi m equal to qm. Fpm is essentially the part of the nonlinearity in the interval IP. So because you have to do it locally, and then you have to glue it together. So psi m is monotone inside the interval, then you can invert it, and then you have to solve this equation, and the continuity at critical points, you have it by playing with initial conditions. So essentially you do it inductively. So you construct f in the first interval, you have f1, then you choose you pass to the second interval, and you put an initial condition in such a way that you attach in SES way, and so on. So that's the way of constructing the nonlinearity. And in the end, so if you, so this is a way to, this is an expression for the nonlinearity in which you glue together what you did in any interval. So actually, so the picture is the following. So you, in any interval, so you are here between two critical points, here decreasing, here increasing. So you construct these, and then you pass to the next interval by gluing it together in a CS way. And here you solve a Cauchy problem in such a way that you put that you have CS continuity, so you have to put appropriate initial conditions in order to have CS continuity. Okay, then the question is that so this is what I did is at unperturbed level. So at unperturbed level, you have like this nonlinearity. Actually, you want to study perturbation of this shear flow because you want to construct the traveling quasi-periodic waves in X. But then you have a problem. If you perturb this and you choose the nonlinearity that you constructed at the unperturbed level, you lose continuity at critical points. So there is something more to be done, but this is very technical. I don't want to enter in details, but essentially you have to modify the nonlinearity that you construct at the unperturbed level. This is really like a modification. I mean, it's this is really like a modification, but it introduces an error in the Laplace equation. So in the end, you solve an elliptic problem with the forcing, essentially. Okay, but this I don't want to enter in details. I want to just summarize the properties of this nonlinearity, which is simply that, okay, essentially outside the critical value, it coincides with the nonlinearity that you constructed at the unperturbed level, and then you have uniform convergence. And that's essentially the way in which one, okay, accommodate the perturbation from the shear flow. Okay, and then in the end, you have to solve. How much time do I have?
5 minutes.
5 minutes. Okay, so I go to the statement fast. So essentially, you solve the Laplace equation for with this modified nonlinearity, which is this one, and I think I can comment a little bit the statement, which is the following. So the precise statement is give me the number of frequency and give me some initial datum, essentially, that parameterizes my solution. Then for time regularity, high and for epsilon small enough, there exists a counter set of parameters which are in an interval. So E is recall that is the depth of the potential well. And actually the frequencies are parameterized by the depth of the potential well. Okay, so the parameter that I choose in order to cut away resonances is the depth of the potential well. Okay, so this is a Borel set of asymptotically full Lebesgue measure, in the sense that when the amplitude of the wave goes to 0, the measure of this Borel set goes to the full measure of the interval, and then you have an asymptotic of the quasi-periodic solution that you find. So you have quasi-periodic solution with frequencies which are omega tilde E, which have this asymptotic. This frequency is actually close to the number of the to the vector of the negative eigenvalues of the potential well. So the frequency of the wave is close to the unperturbed frequency somehow. So this is what happens usually in dynamical systems. And then you are close to QET. Okay, here I write in HS3, you can write HS 7 over 2 minus. And the estimate is the following. You have, you control it by the difference with QET flow, you control by epsilon, which is the amplitude of the perturbation phi epsilon, and 1 over square root of E, where E is the depth of the potential well. Okay, so you are close to QET up to H3, well, up to H7 over 2 minus, actually. And that's the statement. And I think I would stop. Maybe I give you a nice numerical simulation that we did in the case of B-periodic flows. These are generalized cut-ties, in which you have these patterns that form. These are the level sets of the stream function. And I guess I can even stop.
Thank you very much, Riccardo. Are there any questions?
Yeah, so I was thinking about what you said about the R, which you take R big and big and approximate. Yeah. But then at some point you said that you use inch as a parameter
yes,
for the resonances.
Exactly. Then I comment. Okay, then I comment a little bit. So, yeah. Okay, if you consider the linearization at this shear flow, what you have a Laplace, essentially you have a linear Laplace equation where actually you have, okay, dx square, and then you have an operator which acts in y, which is actually really the one with the potential well. Okay, so if you then you can compute, so this operator has like K0 negative eigenvalues, and then the rest of the spectrum is positive. It means that actually a family of solutions of this linear Laplace equation is given by this formula. So you have oscillation with respect to the variable x with these frequencies, okay? It means that you want that these frequencies are not resonant because you want quasi-periodicity. And then how do you do? So this is quite delicate because, okay, first of all, essentially by spectral arguments, you can prove analyticity in the parameter E. But then this is not enough. It is you need something which is called transversality. So it means that if you consider the frequency map, it has not to be contained in any hyperplane. This is transversality, and this is a good thing to prove no resonance by analytic arguments. So, and indeed, what you prove is that okay, the small divisors are like omega dot L, as I mentioned before. It is even in the definition of quasi-periodic. But then, if you prove that one derivative of this is large enough, then you can estimate the level sets of the complement of this set. And you have an estimate like that the bad frequencies are like they have like a small measure, but the key property is to have like this transversality and analyticity.
But then if you take R which is large,
if you take R which is large, It's indeed that's a problem. That's a problem, and one has to see how to. Of course, you can keep the number of negative eigenvalues because E times R is constant. But then it becomes like. And this property we didn't do. We didn't verify what happens in the limit where are. But it's interesting. No?
I couldn't get under which conditions the linearity operator converges to this single web potential. What would have the conditions in which
well, the well potential you have from the beginning, right?
Yes, but you have this which are converging to infinity.
Yeah, it's okay. Yes, that's a bit technical. So there is a formula for the potential, and you can see like by hands that it converges to the potential well. And convergence means uniformly in compact sets outside minus R and R, essentially. So either outside or inside. So it's
convergence is true because of some property
of the explicit expression. So like it is like a formula with hyperbolic cosine. I mean, it's something like this. And then there is a correction which is determined by, is a polynomial determined by Lagrange interpolation theory. I mean, I don't know if it's called. So, but really, you do it is like calculus 1. It's really, you do it by hands. I mean, I don't think that there is a deep reason for which you have. So the deep reason is that you start from the potential well because you want a finite number of negative eigenvalues. So.
Maybe I
Yes,
just,
sure.
What is so special about coed that makes this stuff work? I mean, in just 2 words, just for us to understand that. Why is coed so good compared to?
Well, I would say it is increasing.
Because it's
yeah, and then okay, of course, this perturbation of the coed is not, but
it's important that you start with something big.
Yeah, I think so. I think so. I forgot a little bit the rigidity argument that you proved for Kolmogorov, but I mean. But I mean, the point I didn't remember. I mean, it's so I mean, I remember.
There is a point in being convex also, not only monotone. But yeah, I don't know. It's
not yeah. It's.
So couldn't do it for one sure.
Well, I would say that it could be, yeah, it could be possible, but it could be possible. The point is that you have to guess the starting point, no? Yeah, either the potential or the stream function or. The potential gives you the number of negative eigenvalues. So it gives oscillations.
Yeah, but how you approximate the potential?
How you approximate the potential, it gives you the regularity, yes. So it's. I mean, I cannot say 100% sure it can, but I guess maybe it can be done. I mean, but you need some property of the shear flow, right? I mean, it's. Some hypothesis. I mean, it's
the elliptic problem. Even you're on a monotone shear flow, you don't have a smooth or regular nonlinear function there. Because for coed it's just one.
Really, just one. Yeah. It's
but in general, you just don't have the.
So the usual assumptions that they put on, I don't know, even for the linear investigation. I mean, it's like that. It's something that it's similar to coed. I mean, in the end, the assumptions are I don't remember. I mean, usually there are assumptions on the second derivative. I mean, right?
Yeah, I mean, the first derivative has to be bounded with zero.
Something like that. I mean, it's so in the end, it's it seems something really complicated because it's not explicit. I mean, it's less explicit. So technically, it can be like a mess, but I don't exclude that.
But there's nothing special about this being function that coexistence. It's just that
Well, okay. Here it is.
I mean, what level of importance is that?
Well, here it's special because outside the well is the wet flow, and so this you use, and inside is you use like almost explicit formula. Okay, then I have to think about really in all the proofs where it's really used the explicit formula.
The well already approximates something.
So, yeah. So it's okay.
Okay, if there are no more questions, we can take Riccardo. And we'll be back at noon, so 30 minutes. Coffee and
Now we are even online, but you can share your. I remove from online. Va bene, siamo a 12.04, quindi possiamo anche cominciare. Siamo già online. Prendiamo le palle. Ti metto lo screen. Insomma, la cosa principale è che devi andare avanti e indietro.
Sì, penso sarò...
No, però appunto puoi andarci da qua, guarda dalle freccette, capito? Anche da qua. Freccetta così e freccetta così.
Questo me l'hanno chiesto. Poi l'articolo che stavo pensando.
Okay, so I think we can start. Second speaker today is Augusto del Zotto from Imperial College. They tell us about oscillations in the around statistical right?
Thanks, Michele, and I want to thank the organizer for this nice today's conference. And yes, as the title suggests, I'm going to talk about recent work with Michele. And in particular, I'm going to talk about the stably stratified wet flow in a 3D Gaussian assessment. So I've planned this talk in 3 parts. I will give a brief introduction on what every word in the title of my talk means. And then I'll shift my attention to the homogeneous case. So I'll drop the stratification, I'll drop the density, and I'll mention some feature of the 3D-dimensional wet flow. So we had this talk on the 2D wet flow, and when we're going to other dimension, I have a 3D. And then I'll move back to the original system and discuss the oscillatory nature of the system and how it relates to the feature that I will have presented by them. So without further ado, and this is the Gaussian-esque equation, the Gaussian system. So it's a model for stratified fluids. And it's a model for fluids which are considered to be incompressible, and the density is allowed to be a non-constant density, which force the fluids by means of the gravitational force. So with density, I also refer to temperature. So temperature and density, they play the same role, because ideally a warmer fluid is considered to be lighter, so it's going to tend to go upwards, and the denser fluid is going to be a fluid which temperature is lower. So there's this relation between density and temperature. So throughout the talk, I might say density or temperature, and this is the relation between these 2 quantities. So these are the equations. So the first equation is the Navier-Stokes equation for V, for a velocity in V. P is the scalar pressure, and nu is the kinematic viscosity. And this is coupled to an advection diffusion equation for the temperature in this case. So the second equation, where kappa, is the thermal diffusivity, and this is coupled, as I was saying, through a buoyancy term in blue, which acts on the vertical component on the second component. So imagine that the vertical component is the component of where the gravity acts. And this is where the coupling is made. So ideally what happens is that fluid will move up and down based on the density or the temperature that it has. So in this setting, we want to study the stably stratified wet flow, which is a combination of the wet flow and a stable stratification. So we have some picture. The first one on the right, on the left. Yes, I don't know right and left, but the one on the left is the wet flow. So the wet flow is this flow, as it was mentioned before, which it's a flow that flows parallel to the y equals 0 plane, and it flows faster the further we are from the plane. And it follows one direction. So in a 3-dimensional setting, one can imagine of a channel in which the whole fluid is moving in one direction faster the further we are away from the zero. And then on the right, so not on the left but on the right, there is like a stable stratification setting. So we assume that the density is stratified in such a way that the lighter fluid is on the top, and then we move down, and the denser fluid is on the bottom. Or in the same way, the higher temperature is on the top, and the lower temperature is on the bottom. So what we want to know is combining these two flows, like these two structures, what happens to the dynamic of solution of the equation around this steady state. So what we perform a perturbative argument. We perturb US and theta s. So small u and small theta will be our perturbation, and we can write down the equation for this perturbation, which reads as follows. So I want to briefly comment this equation. So we have time derivative, and then the y dx term that appears in every equation is coming from the linearization, the perturbation around the wet flow, and also u2 in the first component is coming from the nonlinear terms u dot grad, u dot nabla, and it's coming from the wet flow. And then notice that there is this square root of alpha g appearing multiplying theta in the second equation, and multiplying U2 in the last equation. This comes from the perturbation around the stable stratification. This number, I'll define it as beta, and is known as the Brun-Weisala frequency, and it's the frequency at which objects will oscillate in a fluid once perturbed. So imagine to have a particle or a mass of fluid that gets moved from its steady position. So it's unperturbed. You move it up, then we tend to move down due to the gravity, and then but not in the same position as before. So we go below the steady position, and we tend to move upwards again, and this will create an oscillatory. So I add a nice picture here. So this is some internal waves, some patterns that can form in atmospheric motion. So imagine to have the air is flowing and encounters an object that can be a mountain, for example. This will perturb the flow and generate oscillation. And this oscillation, when the air will go up, will create some clouds. Then they will disappear once the oscillation goes down, and then we create these starting patterns. But patterns like this can be observed also in ocean, in currents of the ocean, or in channels in deep water level. So it's very geophysical application, let's say. So now this is all I wanted to say. So I'll just drop the certification and I'll move on the homogeneous case. So I'll just present some result of the three-dimensional wave flow. So I'll write here the equation for the perturbation. So here beta is 0, so there's no beta, there's no density, no temperature. So but the term from the linearization of the equator are there, and moreover the pressure has a linear term, which is 2dx, and a nonlinear term. Some preliminaries for the analysis are the following new variable, which is q, which is in a three-dimensional setting, plays the role of the vorticity, more or less. And this is introduced to exploit a useful cancellation that occurs between the transport term, y dx, and the linear part of the pressure. And I've put it here. So if we consider the equation for q, which is the Laplacian of u, it just breaks down to dtq plus y dxq equal to Laplacian of q. And then if we perform the following linear change of variables, which is none other than following the Couette flow. So we put ourselves in a framework for which we follow the Couette flow. What we obtain is that this equation actually becomes the heat equation for Q. What happens as well is that all the differential operator will depend on time, and this will play a role in the analysis that I'm presenting. So the first feature I want to address is the so-called lift-up effect. So we introduce this notation. So phi 0 is the x average of function phi, and phi nec is phi minus the average. So these are referred as tricks or zero modes, because if the x average is none other than the k equals 0 mode, if we consider the Fourier transform in x, and the solution of this tricks, so solution independent of x, satisfies the following system, which is ith equation for the second and third component, and the first equation is actually the ith equation forced linearly by the second component of it. This implies that there is a growth of the first component, and the growth is linear in time. So what happens is that for small time, so order nu to the -1, we have a growth of for example, the norm of the energy. So this is an instability of a linear instability of this system. And I have this picture here that more or less try to explain what is going on. So we have these tricks that are moving horizontally, And there's some vorticity filaments that are stretched and compressed, then tends to persist and tends to lift up the whole fluid. That's why it's called lift up. And this is something that in the two-dimensional case is not present because of incompressibility. Just to mention. This is a first thing I want to mention, and this is and that was referred to the zero mode, so or the states. So now we move on the non-zero mode, so the PNAC, and we have the implicit damping that has been addressed before in the previous talk as well. And this is a stability mechanism that, of course, in the implicit case, also in the implicit case, and is due to the fact that there is the fast vorticity mixing due to the quad flow that push energy and entropy to high frequency that then are being damped by the Biot-Savart law. And in this case, in the 3D quad flow, only U2 undergoes this implicit damping, and this is due to incompressibility. But in the 2D case, for example, U1 will converge to a streak, U10, because due to incompressibility, if U2 decays like T square, for example, then U1 decays like 1 over T. It's possible to recover this event. So the idea here is to use the fact that now the linear operator, the nabla L, the gradient linear, has some time decay, so we can extract time by paying regularity. So this is the formula, like minus gradient L minus 1, we can extract the T squared decay by paying 2 derivatives. So one has this following formula, so the HS normal V2 neck, because can be bound and it can be extracted as squared. So for U2 in the 3-dimensional quad flow, we have implicit damping of a rate proportional to -2. Something that I can add is, for example, if nu is 0, the equation for Q, the last equation is actually 0, is dtq equals 0, so Q is conserved. So U2 is actually, instead of Q, we can put Q initially, or the GK, for example. Together with implicit damping, I will present briefly the enhanced dissipation phenomenon, and this is a phenomenon which uses the mixing property of a fluid to enhance the dissipation rate. So the normal dissipation rate, or the natural dissipation rate that we have, is the one of the heat equation, which is nu to the -1. But what we can do is using this mixing that occurs in the fluid to have a faster dissipation rate. And this is due to the fact that the fluid is pushing energy to high frequency that are then dissipated faster. So for the quad flow, this rate is proportional to nu to the -1/3, and there is a very easy computation that someone can do. So considering this Fourier toy model, so k is the k, eta, L are my Fourier variables for x, y, and z. So I recall that x and z are periodic, and y is in the whole R. So we're in the unbounded channel case. So we have this dtf neck is equal to -nu, and this is the Laplacian L in Fourier variables. So one has this ODE that can solve, and thanks to the bound for the lower bound for this integral, we can have an explicit rate of decay, which is nu tq times the constant. So nu to the -1. Last but not least, all of these that I said now were linear feature. And now I'll pass to something that is nonlinear, which is the transition threshold. So ideally, the transition threshold refers to establish how big a perturbation can be in order for the flow, for the nonlinear flow, to converge back to the original state. And this can be done comparing to the viscosity coefficient. So ideally, one has a norm, a space x, an initial datum u initial, and what we want to find is an exponent gamma, such that if the norm of the initial perturbation is smaller than gamma, then we have stability, long time stability, so converging back to steady state. And if the norm is bigger than this new to the gamma, then we have instability. If we're able to prove for a specific gamma both of these statements, then we have that gamma is the transition threshold exponent. Otherwise, we just have a lower or upper bound. So for Sobolev space, when X is a Sobolev space for the 3D quad flow, it is known that gamma is at most 1. And this is a result by Wayside. Nice. So keeping this in mind,
I would say it's exactly 1 because of the defect.
yes. So with all this in mind, we'll go back to the non-homogeneous case. And so the non-homogeneous case, I want to address a couple of motivations. So the oscillation I mentioned before were used in other contexts for studying some of the features that I just mentioned. For example, in the three-dimensional quad flow, in the MHD equation, quad with an homogeneous magnetic field, has been proved that these oscillations that are created by combining the magnetic flow with the magnetic field with the quad flow, they suppress the lift-up effect. So we hope that also in this case, combining quad flow and a stable stratification will help us dealing with this effect. And another motivation is that in the result of Roberta and Michele, this oscillation has been used to prove indecisive damping, linear and nonlinear, around quad flow with a stable stratification. So, and the structure of the paper actually is very, very similar, if not the same, to the three-dimensional case I'll talk about afterwards. So in their case, in the two-dimensional vorticity plays the same role as Q, as my Laplacian of U2. So what is the role of this oscillation in this case? So the first, okay. So before presenting the result we have, I want to show how this oscillation appears, because someone maybe wants to see some sign of design, see the oscillation in the system. That's what I think when I think about oscillation. So, so recall the linear change of coordinate. We're following the flow, and we have the new variable Q that plays the role of the vorticity, more or less. So what we do, we focus on the two equations, one for U2 and one for theta, because those are the ones that are coupled together. And in this new setting, they break down and they just look like this. So we have dtq, beta, multiplies the Laplacian without the dy of theta, and then we have the dissipation term. And for theta, we have the same, but with a minus sign multiplied by beta and q. I don't know why there's a 2. There shouldn't be a 2 on q, but and then we have dissipation again. So what we notice is that the plus and minus sign has some sort of oscillators, gives some sort of oscillating structure of to the system. So whenever beta is positive, there's oscillation in the system. And this will be translated then to U1 and U3, because I wrote here the equation for U1 and U3. These are the ones forced by Q and theta. They appear in here. So, but one wants to be even more specific, and so can introduce some variables that symmetrize the system. And this has been done by Roberta and Michele. So introducing these two variables symmetrize the system, so you can clearly see that the structure we obtain is the same, that just one sign is changing. And then if we further consider the zero mode, so we take the x average, we get rid of the first term, and what we obtain is exactly the same term with a minus and plus sign. So this is oscillation. So if we remove, for example, the right-hand side, we just get oscillation. So nice. So let's start to address the feature that I mentioned before with the lift-up. So this oscillation actually helps us to remove the lift-up. So we have the first term. So as soon as we have pairing, so beta is positive, Then the solution of the zero mode system will dissipate with the heat dissipation rate, which is the minimum between nu and kappa. And here there's a less or equal with a small constant beta, and this constant beta appears in the only in the first inequality for the first component as 1 over beta multiplying u2 and theta. And this, I want to remark that this relates to the fact that if beta is 0, then this constant explodes to plus infinity because the lift up is there. So this is a sign that should be okay. Anyway, so and I'll just sketch the proof briefly. So what we do for this case is just write the system in Fourier. So eta and L, so k is equal 0, so it's not here. And what we have is that we obtain a completely solvable ODE system of ODEs. So we can write the explicit solution and get from here the dissipation rate and the suppression of the impact effect. So if you focus just on the component of u2 and theta, change of coordinates and everything, what we get is that if we multiply the initial data by this matrix, which is the explicit solution, we get the oscillation unit. So there's the presence of cosine, hyperbolic cosine and sine that hints some sort of oscillation. And this oscillation can be highlighted in the special case when nu is equal kappa. So my little coefficient A is equal to 0, and so C is imaginary, and makes all the hyperbolic cosine and sine to be actual cosine and sine. So the final solution reads like Q tilde 0 and theta tilde 0, they are oscillating like sine of beta. And beta appears inside, so it's the frequency of oscillation. Okay, always in the special case nu equal kappa, there's a faster way to see that the constant depending on beta is 1 over beta. And if you notice the first equation and the last equation, if I multiply the first equation by beta and I add the last equation, then the beta u20 cancels out. So we have this relation between u1 and theta 0, which is beta u1 plus theta 0, and this satisfies the beta equation. So if theta oscillates, then u1 oscillates, and if I want to translate the bounds from b0 to u10, then I have to divide by beta, and hence I have 1 over beta. So okay, and then we move on non-zero effects. So this is the second theorem we prove, and this is damping and enhanced dissipation in this setting. So here we have to assume that beta is bigger than 1/2, and this is due to the Mayer-Howard theorem for stable stratified fluids. And yes, so we have also to assume that nu and kappa, they are not too far apart. They are more or less comparable based on beta, on the size of beta. This is like more a technical details to get the proof. And then we have the rate lambda nu kappa is proportional to the minimum between nu and kappa times a constant times a factor, and we obtain enhanced dissipation with the rate lambda nu kappa 1/3 for u1, u2, u3, and theta. And moreover, we obtain enhanced implicit damping for u2 neck and theta neck. But this time we get it a bit weaker than the one only for the 3D quad flow, since 3D quad flow had t cube and we have 3 to the 3/2. And you can see this as some of this is just going to the theta variable. So 1/2 is passing from u2 to theta because of this pairing and this oscillation. So the proof runs as follows, and it's very similar to the one of Michele and Roberta. And we define a pointwise energy function, which is the following. So it has a mixed term here, the 1 over beta mixed term, that is done to, so I just quickly go back to this. So the energy function is defined based on the system of in the middle. So it balances out all the term. And sorry about this quickly changing of slides, but yeah. So what we can prove is that, or what is proved is that this functional is coercive for beta greater than 1/2, and also there's some time decay for the derivative of this functional. So once we integrate, we use the same trick of the Quet flow here to have lambda nu kappa t cube as the thing. So once we have everything, we can prove, yes. To obtain an anticipation, we use the trick that I just mentioned, and we get that q tilde neck and theta tilde neck that are the symmetrized variable, ADK with an anticipation rate lambda nu kappa minus 1/3. And then to obtain implicit damping, we can translate again this inequality in the original variables, and we use the same trick of paying regularity to obtain time decay. And since recall here that we have that the new symmetrized variables are not Laplacian -1 anymore, but it's Laplacian to the -3/4, then I can extract the t to the -3/2 and t to the -1/2. And that's why we have 3/2 and 3/1/2. Okay. And last but not least, the last but not least, this transition but we're able to prove that the related highest of the regularity, then we can prove that if the initial relation is smaller than mu, so the solution of our time satisfies the situation estimate, the anticipation, the last one is the anticipation, and then for the zero point also next, so I want to quickly just to finish up, talk about the two. So without going too much into this, and the tools we use. So today we mimic what we did in the schematic, in the so the first result. So we use the function and the schematic variable. But we use a real multiplier that is serving the function. This real multiplier is defined as A, which is made out of 3 parts. The first one is the solid regularity. So modulus of carrier for us. And the second part is that to the 1 minus 1 to the 1/30 is an encapsulated the anticipation rate, and n is a so-called Gauss multiplier, and Gauss multiplier goes because there is a constant positive, this is constant multiplier from 0, and then it was 1 so it's a constant, so it's a Gauss. And that is defined by 3 terms, 1 and 2 and 3. They are defined in the following way to represent equation. And the first one, the first one is designed to capture the transition between the anticipation regime and the dissipation regime. The second one is designed to deal with the derivative of the mixed term in the energy function. But the third one is designed to absorb eventual time decay we have in the analytical limit. And whenever we can structure the data, so we get rid of this main structural stability for the linear. Okay, and the proof is based on the bootstrap strategy. So we assume that after time t, this inequality holds, and then x is one of our variables. Then we want to prove that actually this inequality holds with two intervals, and this will imply that t is to say is that this analysis is very delicate since there is some sort of interaction between these, for example, UI and UJ, which can be done in different ways. So, for example, there is nonlinear interaction, or non-zero interaction, zero non-zero, and zero interaction. So, if we analyze this frequency by frequency, for example, we can have forcing of frequency depending on where these nonlinear terms are interacting between each other. And I just wrote down an example. For example, the nonlinear pressure term for Q2 reads as follows, and it has to be studied dividing the case like by frequency interaction and also by indices interaction. So what happens when U2 interacts with U1, what happens when U2 neck interacts with 1, 0, and so on and so forth. Okay, but ideally, what we want is that from an energy estimate, we get that the previous quantity here, I put Q tilde, is bounded by the initial datum, which is smaller than epsilon squared by hypothesis, and then the integral of the scalar product between AQ and the nonlinear term will be bounded by nu to the minus gamma epsilon times epsilon squared. So here you see that to establish gamma, that is will be the threshold exponent, we just need to find out what is the biggest nu to the minus gamma we obtain there, so the biggest loss. And this is done ideally by distributing derivatives, that things that appear. So for example, here we have minus Laplacian L minus 1/4, and then a dyl, so, and what derivatives. So we want to distribute this on all the terms that appears in the scalar product and obtain an estimate of this form. So the first term is the energy, L infinity in time. Second term is the Gauss multiplier that encapsulates some time decay. Third term refers to the enhanced dissipation, and the fourth term to the dissipation. And then we bound this paying accordingly to, and we pay some power of nu, and we get like nu for the dissipation, then Laplacian is missing, and then x is missing also in the last equation, amazing. And then for the enhanced dissipation, we pay a lower price because this will have a rate as a better rate. And this is how the proof goes. And then I want to finish with some heuristic on why the threshold is 1 in this case, and we obtain 1. So ideally, the threshold is determined by the largest instability. And for the 3D quad flow is the lift-up effect. But here is removed because of the oscillations. So the main instability here is the biggest growth in time of the nonlinear term. So because what happens is that we have to control these nonlinear terms before the dissipation starts, start like killing everything, or the enhanced dissipation. So for the nonlinear term, for example, there's some terms, for example, NLP. So this is the interaction between U3 and U2. One of them is the 0 and one is the non-zero. And this grows like t to the 3 half. So what we can do is say that before the enhanced dissipation starts, this will grow like t over 3 over 2. And if we integrate this between 0 and the time of the enhanced dissipation time, this will give us nu to the minus 5 over 6. So this proves that actually for the nonlinear terms which enhance dissipate, the non-zero nonlinear terms that enhance dissipate, that have enhanced dissipation, the threshold could be lower than 1. But in the zero mode, we don't have time drop, we don't have time decay because the k is 0, so there's no time. There's no enhanced dissipation, so whenever there is 0-0 interaction, the best we can do is just bound between 0 and nu to the minus 1 and have nu to the minus 1. So yeah, so this is why. So ideally, one would like to have some more decay in the zero mode, maybe using some other sort of technique. But yes, and this was everything I wanted to say. So yeah, thanks.
Thanks, Augusto. Are there any questions? If I understood correctly, your y variable
is defined in the real line,
Yes.
would it make a difference if you consider only the positive real line? So from 0 to infinity some boundary conditions, so that because otherwise, like because of the temperature, if you have negative twice, it is also lifted like down, 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 and each time it's going faster and faster in different things. And have you thought about only consider the positive real line?
No,
Something like that?
because every time there's a boundary, there's more problem next to the boundary. So taking the whole real line get rid of this issue, and I've never thought about taking a boundary and see what happens. But maybe it could be interesting.
Also, it's my question. And if you drop out kappa, because sometimes I see less without the diffusibility density.
So some of these results hold, for example, if nu and kappa is 0, they have some result, and I guess you can obtain the same. There's still some result with kappa equals 0 and nu not 0. Also, like for example, just in one component in 2D. In 3D, I am not sure.
Is it technical or just we don't know?
Let's say the oscillation are there even if nu and kappa is 0, or for the lift up, for example. So I guess, like for example, yes, if you put nu and kappa 0, this you don't have a dissipation rate, but you will have oscillation that will transfer to the original variable. And even if you put kappa equals 0, you can obtain a similar result. I think it's doable.
Yeah, so just, I don't know if you just mentioned at the end, so I don't know if you have an idea, but when you say another way to treat the zero mode.
Sorry?
Because-
So in this case, we have the unbounded channels, so we have y in the whole R. So hopefully there might be a way to extract decay through dispersive estimates, since we have oscillation in R. That I think it's the best way to exploit this extra structure that we have. But yes, I think this is still a work in progress. It might be update you soon, but ideally I think it's doable. I think there's some more information to be extracted.
It would be less.
Yes, yeah. Because ideally, what someone can have is is that here we're just integrating between 0 and nu minus 1 some negative power of time, like for example t to the minus 1/3, which gives t to the 2/3, which is nu to the minus 2/3. So we'll help bring down the pressure. So any time decay in the 0 mode, which is independent of nu in this case, because these oscillations are independent of nu, will help to lower the threshold. Because apparently now the main issue is the 0-0 mode interaction for the 0 mode analysis. But yes, it's just because it's unbounded. So there's some result in R3 by Klaus Wittmeyer. They use this dispersion relation to prove it. 2 and 3D as well.
Yeah, but in the rotation.
Yes. No. It's like a short short time existence. So they're like increasing the. Yes.
Yeah.
Yes. So yeah, but they are in a 3, so there's no dispersion. But if maybe with one direction, maybe there's hope to have at least a bit of decay.
Okay, now we can thank Augusto. And we are back here.
buenas solución.
Adesso metti il programma così, vediamo se si vede.
Adesso devo aprire.
Vediamo se si vede. Lo vedo da qui, Lo guardo da qui.
Che lui prende il controllo di quello adesso, praticamente.
Ha preso il controllo di quello, però non so se quello che fa.
Quindi anche il microfono.
Sì, c'ha tutto, sì. Vediamo. No, che sta facendo? No, tu non devi mettere, non devi aprire StreamYard, no. Tu devi aprire semplicemente il programma di scrittura e basta. Perché stiamo usando quello lì, vedi? Ah. Aspetta. No, lo vedi? Non lo vedo.
No, infatti si vede lo schermo, però non si vede.
Si vede, guarda, si vede lo schermo, ma
Si vede quello che c'è sotto, diciamo.
sì, non vede questo, è come se gli fosse trasparente.
Se scrivo qualcosa qua non
No.
No, vede solo lì.
Allora, stacchiamo questo e facciamo l'ultima prova e poi si fa su. No, e poi semplicemente si scrive qui, perché lì lo vedo la persona. Sì, magari si può mettere a questo. E lei scrive lì che si e chi sta in Io streaming no, posso fargli molto di più. Gli possiamo mettere la videocamera sul coso. No, la mettiamo lì semplicemente così. Vedi, se tu si mette lì, se si mette sotto, aspetta, la bisogna mettere qua, se no lì. A parte la posso fissare, però voi vedete questa lavagna qui.
Sì, però
adesso sì.
Se parlo io qua, da qui, uno scrive da questo punto qui, si vede?
Sì, un po' spostato, però.
No, però non si vede proprio.
Possiamo mettere al centro?
È troppo chiaro.
È troppo chiaro. No, perché sotto qualcosa non si vede niente.
Si vede solo bianco.
Se io mi metto qua che dovrebbe inquadrarmi,
Certo.
però tu vedi quello che sto scrivendo.
No, non si vede niente, no. È troppo chiaro. Spegnendo,
ma non sa che non prende proprio.
Perché questo si può anche bloccare. Si può bloccare, no? Mi sembra vero.
La fissa insieme.
Mode. C'è un modo fisso per vederlo. Mi ricordo, sai. Questo lock. Fa il lock qua, vedi? Non era questo qua. L'ha fissato tutto bene?
Sì, prova a spostarti. Sì,
Io sposto,
ora l'ha fissato.
I'll send you a link.
Però non so se disegnando riesco.
No.
Vedi qualcosa? Spegne la luce che dice? No, a parte prima bisogna vedere se si vede. La luna è qua che.
Ma quella è la luce sotto. C'è anche il proietto.
Ma quindi non funziona il sharing?
No, non funziona che non si vede.
Vabbè, ma c'è qualcuno connesso?
No.
Allora?
No, stavamo vedendo, si scrivendo lì, si vede quella.
No, una persona. Che forse so io. No, adesso si vede lì. Dove sta il tuo. Prova a scrivere lì sopra. No, devi scrivere lì per forza. Abbiamo fissato pure questo. Questo qualcuno se lo sta dimenticando chi è Michele forse.
No, anche le note. Che sto iPad e tutto. Vuoi fare? Una persona, ma secondo me sei te.
Che cosa?
Chi è una persona? Sei te.
Ridolfo. No, perché questo qua è uscito. Ridolfo. No, Sara Teneri, implacabile. Non siamo online in questo momento, tra l'altro. Adesso ho chiuso il mio, allora può essere lei che non sta Sara Teneri.
Sì, sai, perché lei.
Perché mi sono staccato io.
Ci sarà, può essere, c'è sta, ma da 3 persone lì.
Ma scusa, allora, ci sono due modi. Abbiamo due modi. Uno, quella cosa che ha detto lei, che mettiamo su quel blackboard.
Ma dove scrivi però?
Sul fugato. Perché quello funziona. Vediamo come si fa. L'ho tolto. Il resto lo guardo io.
Sì.
Quell'integrale lì, quella grandezza,
Il resto lo guardo io.
è che così
Okay. Are you sure you can do that?
I will see if it disconnects.
No, you try to avoid to be disconnected.
I'll say it's off.
Ci sei riuscito.
Quindi io dovrei fare nulla meno 2 esercizi prima che poi comincio a decadere. Magari non ha senso quello che dico.
Ah, io ho fissato questo qua invece.
Sono d'accordo che se poi invece
Ok, sì, avevo messo ho bloccato con l'occhietto, no? Sì, invece va bene così. Ok, perfetto. You have to speak quite high for your voice.
For the streaming.
Yeah. I can put here the microphone. So you are just in front of. That's better you sit down during the talk.
Yeah.
Right.
What else?
Yeah. Try to speak
Yes, like this.
something a bit more.
A bit more than like this. So yeah.
Something because you cannot see what I'm transmitting. So people are looking this one, but in general, on the web they see this one.
Okay.
Okay. So they see your blackboard. When you speak, people speaking, they just turn on the people.
Yeah, I noticed that.
So that's why. So you have to speak, and you have the only one.
Otherwise, it doesn't show me, but it's okay.
Yeah, no, but it's also the mic because you have a not very loud voice. So.
Okay, if I speak like this, it's already low.
Yeah, is it still working or?
I hope so.
That means you have not using the. Okay, good. See, but again disconnecting you. Okay, here, this one. This one. Okay. Why? I don't understood why you are disconnecting yourself.
So the thing is that in the tablets, when you do this, it goes to the previous step. And I was trying to pull a line,
Yeah.
and I was
You have to avoid to
going
touch
to,
the screen. Okay.
There are many things complicated. You can bring this closer to me.
What?
Like this is fine.
No, too much because also I need your face. Otherwise, it's not a good. That's fine. Non sono riuscito a mutare anche. Adesso stiamo parlando invece di
58, 57.
Not before 33.
Ok, apposto. Il mio è anche aperto. Ok, grazie.
Forse mi devo spostare da là.
Potenti mezzi di tecnica.
Okay, so then we start again the afternoon session. So the first speaker is Angeliki Menegaki from Imperial College London, and she will talk about the full weight kinetic equation.
Thank you very much for having me here, back in Rome. Always very happy to be in Rome. So yes, I'm going to present some new results on the wave kinetic equation when you have 4 waves interacting. So this is an equation that it arises in wave turbulence theory, in weak wave turbulence theory. And what I'm going to be doing is to study the stability in L2 around some of the equilibrium steady state solutions of this equation. So I'm going to motivate the problem and also have to sit down. Okay. Something I'm not used to. Because I guess most of you is not very familiar with the field, the specific question. Okay. So the kinetic wave equation, I will call it KWE, is a central component of wave turbulence theory. Okay. And sorry. No, it's okay. It's just a scan QR code every now and then. Okay, so the equation arises as a kinetic limit, a high frequency limit, from time reversible, typically wave or dispersive systems. Okay, like this. Where you have waves interacting non-linearly. Okay. And the solution of such equation, it's supposed to predict the distribution of the average energy in your frequency space. In your frequency space. Okay, I will say more details about this in a minute. Okay, so the theory predicts that the macroscopic behavior, so the macroscopic behavior in this case will be the wave kinetic equation, which is a mesoscopic level, but okay, we'll call it macro. And the microscopic level is typically a nonlinear dispersive, say the NLS, for example, equation or wave system. And it's supposed to predict the macroscopic behavior of such nonlinear wave or dispersive systems is given by this wave kinetic equation. So this wave equation kinetically approximates the average distribution of energy among the available wave numbers. Okay, so now this theory, the way I understand it better, and I think most of you as well, is through the analogy of the particle theory of the kinetic theory of particles due to Boltzmann. Okay, so I will give you the analogies. Okay, so this theory can be seen as a parallel theory for waves rather than particles. Like this? Yeah, I can see it here.
It's okay. The rest thing.
Yeah, maybe it's okay. Just try to before.
But no, you can just okay. Yeah. I have to do it in both. Okay, I will do it in both devices. So yeah, again, so this theory can be seen as a parallel theory for waves rather than particles, which is as fundamental as particles. So on the one hand, we have okay, let me do this. No. Sorry for that. I will not do this movement again. Okay, so on the one hand, we have the kinetic theory for particles. And the main object here is the Boltzmann equation.
I have to move the screen. Okay.
Okay, let me write in this. In this. Okay, so yeah, on the other hand, you have the Boltzmann equation, and on the other hand, you have the wave kinetic theory, which was developed due to Peierls a little bit later than Boltzmann, say 29. And other big names in this field, I mean, the fathers and how the field is also, say, I will cite Hasselmann for water waves, and Zakharov, who studied the non-equilibrium solutions. Okay. Here is the spot. Okay. Okay, so in Boltzmann, imagine that, okay, we have n particles of radius r, so say you're in a box. You have particles colliding with radius positive, and we assume elastic collision, so the energy is conserved. And now typical assumption here is that the initial state are random and independent variables. Okay. And say its particle has initial density f0, and this is a function that depends on space and velocity, space x, velocity v. Okay, now we want to study the evolution of the system, but we have n particles, so it's a lot of trajectories to study. So what we do is to see this statistically. And so we go through a kinetic description. Okay, I will go here. And so if we say we look at the one particle density, which I will call F1, which is a function of space, time, and velocity. And this will be basically the probability of finding a particle at position x with velocity v. Okay. And now what we want to do is to take the limit as n goes to infinity, the number of particles to infinity, and the radius of the particles going to 0 at the same time. So this is the Boltzmann, the so-called Boltzmann-Grad limit, and we take this limit in a specific regime. It's a low-density regime. We want n times the radius, dimension -1, to be of order 1. Okay, so we can call this gamma. Okay, and now it's known that for short times at least, the Boltzmann equation is the effective dynamics of this F1 function. Yeah. It's impossible. Okay, I will. No, it's okay. So imagine it's just Boltzmann equation there. Okay. Which reads as follows. Okay, so you have the time evolution, you have the kinetic part, the transport part. And then the right-hand side is quadratic nonlinearity collision kernel, describes the collisions. Okay, so this is the collisions of the particles. And this is the transport part of the equation. Okay, and this approximation holds for times of order O to the gamma -1. Okay.
Or maybe you can.
So I will do, yeah.
Yeah, just below. Of this vision here.
Okay. Okay, so this result now is known since Lanford, 75, and it was more recently proven more rigorously by Gallagher, Lawson Raymond, and text here. No, now you have to press the Santa Claus. Okay, so the approximation of the Boltzmann equation approximates well the dynamics in the microscopic level is known up to the kinetic time scale, which is of order gamma to the -1. And now, okay, I will write here the parallel theory for waves. I'll do it. Like this. Okay. Okay, so here instead of a large number of particles, we have many waves interacting. And here, okay, we work on the frequency space. So each wave is represented by Fourier mode of the solution of your dispersive system, of your nonlinear dispersive system. Okay. And typically we're in a box of size L. Okay. And what we want to take here is the limit as L goes to infinity. So this is the analogous of taking the limit as the limit of number of particles going to infinity. And the collisions here are given by the nonlinearity in the dispersive system. Okay, and the dispersive system that we look at usually, I mean, you can look at many microscopic systems, but the derivation is done for the NLS. So you have IDT. Okay, and here you have the size of the nonlinearity alpha. And some initial conditions. And okay, so we assume that X, our space, is in the periodic d-dimensional box, size L. So this is like L times the 0, 1, d. Okay, and now, as in the Boltzmann case, we start with initial data. Okay, so the question here is to study the solutions of this equation. Okay, but this is very hard deterministically. You have a very rich phenomenology in this type of equations. So what we do is to add some initial data that are randomly distributed, and to look at the statistical description as in the Boltzmann case. So we start. So can you read this? Oh, it's fine. And here K runs over the integers. And what we assume, okay, so we want to have random and independent Fourier mode. So what we assume here for the U initial hat is that this, okay, this is, say, some random variables that are, say, like the Gaussians, for example. Okay. And times some smooth function. So this is, say, a Schwarz function. Okay, so such data are called well-prepared initial data. Because if you now compute the variance of U initial K, this will give exactly the F initial. Okay. And this F initial will be our initial state of the wave kinetic, of the Cauchy problem or the wave kinetic equation. Okay, so the goal now is to understand the distribution of the Fourier modes at later times. And what we're going to be taking as a limit here is, as I said, L to infinity. And at the same time, the size of the nonlinearity alpha, this one, to 0. So this plays the role of n to infinity, r to 0. Okay. And the effective dynamics of this limit, effective, is then given by the wave kinetic equation. Okay. Okay. Which reads as follows. So here we have the time evolution, ftk. And here we have the collision kernel, which in this case it's not quadratic, but it's a cubic nonlinearity. Say initial data, as I said, set initial. And okay, so the collision kernel, the collision operator is given by the following. So you have an integral. Actually, it's 3 integrals. Okay, so K1, K2, K3, and K are the 4 waves. We have 4 because we start with a cubic nonlinearity in the NLS. We also have, say, I will write in more generality, a cross section here that it's K, K1, K2, K3 to some power beta, beta over 2. And now the collisions are all taking place in the resonant manifold. So we have 2 Diracs, okay, where omega it's like this. Where I denote with omega this relation. Okay, I will explain now the notation. It's K3. And with sigma, minus K3. And here, omega is the dispersion relation of the system. Okay, so for given K, omega K is the dispersion relation. And okay, so now the integral is over K1, K2, K3. So I wish you could see it all, but I don't think it's possible. Okay. Okay, and this beta here is just a parameter. So when this beta is 0, this corresponds to when we start from just the cubic NLS in the microscopic level. For general beta, it's we can allow some more general nonlinearities. For example, we can have, okay, so beta equals 0 is the cubic. And more generally, you can allow this kind of derivatives. Acting on U. So, Okay, it's a model that was suggested by Maida some years ago.
Wait, what is point there? Okay, one case.
So this is beta. Beta.
Beta over 2.
Yeah. So this and this are all beta.
Okay.
Okay, now about this rigorous derivation of this equation, there was a series of papers lately, so it's now proven up to the kinetic time scale, as also holds for the Boltzmann equation. So I will cite some people in this part. My time is over. Okay.
Just up. You see that up.
Right. Okay, so first Pyers, who was the first person who suggested the whole theory, so proposed the derivation when we start from the so-called FPU chains, FPUT chains. This is like harmonic, anharmonic. So it's harmonic crystal, harmonic oscillator chains, and you allow some weak anharmonicities. And here, in this case, we expect to derive a three-wave equation. So you have three waves interacting. Okay, and there is also a more recent review by Spohn in this direction. Okay, and now more recently, it all started by Lucarin and Spohn when they looked at the NLS, as I described above, and they derived the equation at equilibrium. Okay, so that was around 2010. So here they started from a discrete NLS. At equilibrium. Then, okay, there was the next big paper was due to Buckmaster, Zerma, Hani, and Shara in 2019. Where they derived the equation, but for very, very small times. They couldn't reach the kinetic time scale. Okay, so that was much lower than the kinetic time scale. And more recently by Deng and Hani, and then, okay, so there was a competition going on between Deng and Hani and then the group around Pierre Germain. So I will cite both, Germain and Sarkozy, where they were reaching the kinetic time scale up some polynomial laws. And eventually was proven by Deng and Hani up to the kinetic time scale. So now the derivation, we know it's true. And the purpose of my talk will be to study the long-term behavior of solutions, okay, given that this equation holds. It's rigid. Okay, so I will start with some basic things. So first, we have the same kind of conservation properties as in the Boltzmann equation. So there is mass, momentum, energy conservation. So this means that if you take the collision operator, this is 0. So, okay, so at least formally you can prove this. You can take a test function and then you can compute, say, for some test function phi. You can compute this. You can use the symmetries given by the resonant manifold. And you can rewrite this as 1/4. Here you have, say, some collision kernel. Okay, we'll write a sigma here. So you have F1, F2, F3. When I write F1, F2, F3, I mean FK1, FK2, FK3. And this is times V1 plus V2 minus V minus V3. Okay, so you can write it in this form. And now you can see that if you take phi to be a constant, this is 0. If you take phi to be k is 0 because of the dispersion, because of the resonant relation, and the same for omega. Okay. Okay, and what you can also see is that you can take the entropy to be okay. So it's not really the entropy; it's like a Lyapunov function here. So you can compute just the logarithm of f, and you can see that this is positive with the same computation as before. So this means that the entropy is increasing, and somehow in the absence of forcing, we expect the system to relax some equilibrium. And this equilibrium in the context of the Boltzmann equation, it's just Maxwellian. Okay, and in this context is the so-called Rayleigh-Jeans equilibrium. Okay, so it's the following. So, which is okay, Rayleigh-Jeans. And it takes this form, so it's 1 over alpha, so some constant here, b times k plus c omega k. And here c is positive, and you want also the denominator to be positive. So you have a family of equilibrium. Okay. So this you can see if you compute in the same way that you see it in the Boltzmann equation. You see where the entropy is getting 0, and it takes this form. Okay. Okay, so this is one of the equilibrium solutions we see, at least one family of equilibrium solutions we see. Yes. Yeah, the logarithm.
But without.
Yes. So this is the thing.
Determined by this
yeah, exactly.
reimbursement. Like,
yeah, here it's a bit different because you can have condensation happening, a finite time blow up, depends on your initial assumptions. And so I will give some state of the art, which it's really not very well. It's not very well understood, but yeah. So either you convert to Dirac, which is the condensation, or you expect to converge to this Rayleigh-Jeans. And now, if you add some forcing, some say on the boundaries of your frequency space and Dirac, you expect to see the so-called Kolmogorov-Zakharov solutions. This you see after a conformal transformation in the equation also. Okay, so there are also some spatial stationary solutions, which are the non-equilibrium ones. So the Rayleigh-Jeans are equilibrium. There the flux is 0. You're on the thermodynamic equilibrium. And on the Kolmogorov-Zakharov, one can observe some non-zero flux, energy and mass flux. And it takes, we can see two of them. So you can see a solution looks like k to the minus 7 over 6 and k to the minus 3 over 2. And this one corresponds to when you have a constant non-zero flux with a mass going from infinity to 0. So all the mass is concentrating to 0. And in this case, you have a constant flux where the energy is going from 0 to infinity. So you can see cascades of energy and mass. Okay, a direct and an inverse. Okay, and these are the physically interesting scenario because you can see these fluxes, but also, I mean, it's also the interesting scenario mathematically because this kind of behavior, when the fact that the energy is going towards infinity, you have this direct cascade of energy. Somehow reflects the fact that in the NLS, in the microscopic system, the Sobolev norm, you have these results about the arbitrarily large but finite growth of Sobolev norms. And I mean, it's a big open question to understand whether this behavior of the solutions of the NLS is generic, or because we can construct solutions. Okay, so I have these papers by Stefileni, Colliander, Tao, several other people, where they construct solutions that exhibit that their Sobolev norm is arbitrarily large but finite. Okay. And now we don't know whether this is a generic behavior. But in the scenario where statistically you see that the energy is somehow going to infinity, this represents the fact that the Sobolev norm is growing. Okay, but this mathematically is really not very tractable, this case. So the results that exist, I will cite very few papers. So there is a well-posedness result by Escobedo and Velasquez. Around 2013, where they work with radial solutions of this equation, and they show existence of weak solutions, and then they show that there's a finite time blow up if you assume that your initial mass is finite. Okay, it's because since your initial mass is finite, as time goes to infinity, you need your mass to be finite also at later times because mass is conserved. And the only way with this equilibrium, the only way to succeed this is to have a drag. Okay. So under this assumption, you converge to say some drag. And then another result on local well-posedness is due to Zermayo and Esquentran. More recently. Where they prove local well-posedness in L2 and L infinity. Some weighted space. Okay, and there is a forthcoming paper of Zerma and Lau, where they're able to consider more general cross sections. So here this, what am I doing? So for a general vita here. Because typically you take beta to be 0 because it's the simplest case.
So I just wanted to,
Yeah.
I was a little bit confused when I used, we were talking about mass conservation. But then there was mass going from, I was lost a little bit when you.
Yeah, I mean, I'm talking about the thermodynamic equilibrium. It's not, in the cases that are also studied here, it's there is no cascade of mass. Yeah. You need to add this forcing to see the cascade of mass.
Okay.
Okay, so one thing one can do here to study the stability of solutions, okay, whether if you start, say, the idea is to show that, at least for this thermodynamic Rayleigh-Jeans equilibrium, if you start close to this, okay, you will remain close to this. So what am I doing is to take, say, one of them, okay, and to linearize around this. So I'm looking at solutions of this form. And then I'm looking at the evolution of G. This function here. And the equation that this G satisfies is the following. So you have dt of G. Okay, you're again on the reasonable manifold. Here you have the equilibrium taking values at K1, K2, K3. So this is gk1 over f infinity k1 plus gk2 over f infinity k2. Okay, minus g. Okay, and you integrate over k1, k2, k3. And then you have some orders of some other terms of order epsilon. Okay, so you have a linear equation and low order terms. Okay, and now this operator here looks like a lot like the Boltzmann equation on the linearized level. Okay, so this I call L. And so, yeah, you can see that this operator is self-adjoint. Okay. On L2, so this is a difference with the Boltzmann equation where you have self-adjointness on L2 with the weight of the Maxwellian. Here you don't have your L2 flat. And then you can also compute the Dirichlet form. So you take the inner product of Lg times G. And you can see that this is positive. Okay. And this means that the spectrum of L lies on the whole space, but say in the negative, the positive line. Okay, and that the kernel. Okay, that's important that the kernel of L is generated by, is spanned by 1, K, and omega. Okay. So these are belonging in the kernel. Yeah, so far I don't have any. Yeah, so far I don't have any restriction. For my result, I have restrictions. And also, yeah, for the local well posedness, they, yeah, Escobedo and Velasquez and also Germain and Escoutran, they all assume quadratic. Actually, Germain and Escoutran, they generalized a little bit. For the L2, for the L, no, yeah, for the L infinity, for the L2, they need quadratic. Okay, so I have the two main assumptions here. Technical assumptions both. One is that I need a cutoff on the frequencies, so I cannot allow frequencies to go to infinity. So for all my k's, k and ki, for all i's, I need some kc which is finite. So somehow I'm restricted in a box. And on the dispersion relation, I have to assume that it's radial. Okay, it's a radial function. And I can have k squared plus a small perturbation here, sk, with some L infinity bound on S. And also the assumption that omega x over x for positive x is bounded below and above. Okay. This is C1, C2, C3. Okay, one more is that the Hessian of this perturbation is a metric that's positive definite. Okay, so I need the curvature to be not to be degenerate, not to be 0. Okay, so one result on the linearized levels is the following. So you take beta to be 0, bounded frequencies. I call the linearized operator LKC to denote that this acts on the box. Okay. And so what one can show is that the linearized operator is coercive. So you take a G, which is L2, but restricted on a box. And also that does not belong on the kernel of the operator. So it's orthogonal complement of the kernel. So then you have that you can find a gap. So you can find a lambda that depends on this cutoff, which is positive, and for which the Dirichlet form is bounded by the law. Okay, so this is the box. Okay, so this you can do by splitting the operator into a coercive and a compact part. So if you see the operator here, the third term depends only on k. Yes, depends only on k. So this you can take out of the integral, which is on k1, k2, k3, and this is a multiplication operator. Okay, so you can prove that this integral then is positive. So this will be the coercive part of your operator. And then you look at the other three terms, G1, G2, and G3. You gather them together and you prove that this is compact. A way to do this is to take by inspection to see the Hilbert-Smith kernel of this operator and to show that this belongs in L2. And then as Hilbert-Smith operator, you have compactness. And then by Weyl's theorem, you can conclude the existence of a gap for the whole operator, L. Right, but you cannot see exactly, it's not a quantitative proof, it's really qualitative. So you can see the existence of a gap, but you don't know how this depends on KC. So a question the next question is to quantify this, try to quantify this, and to be able to remove the cutoff. Is my time up?
I'll still have
Okay.
5 minutes to maybe 7.
Right, okay. And now, okay, so this is the result on the linearized level, and now one wants to pass to the nonlinear level. So the notion of solution that I'm going to use is the L2 mild solutions. So I'm saying that the solution is L2 mild if, say, for initial data F0, these are in L2, and for Ft, using a Duhamel formulation, you can write it as F0 plus, so you have a time integral yes, and you want this to be in L2 as well. Okay, so given this notion of solution, you can have the following theorem. So again, the same assumptions. Assuming that the linearized operator has an L2 spectral gap, and assuming that your initial data are small in L2, say this bound, for some constant C, positive, lambda is the gap. Then you can have existence of a mild solution and uniqueness. I call it GT. So that the L2 norm of GT is also bounded like this. And when you look at the orthogonal of the kernel, so if I call P the projection on the kernel, so then the kernel of the operator, I mean, so look at the evolution of the function that it's not multiplication of F infinity. Then you have an exponential convergence. So there is like a Bayesian of attraction characterized by an L2 norm. Yes, move again. Yes. Yeah, maybe.
Yeah, so that it could be 1.
So you can remember the last term. And okay, so it's the projection. So if initially we also assume that okay, we don't allow any fluctuations around, so we take this P, the projection of the initial data on the kernel to be just 0, then you have exponential convergence. Okay. Okay, and okay, so in order to prove this, I mean, it's nothing really sophisticated. But the technical part is to control the nonlinearities, which are cubic in L2, which is not trivial.
No.
Yes, yes. So you can write your evolution of the equation. Okay, so you have the linear part, okay, and then you have some quadratic nonlinearities and some cubic nonlinearities. Okay, you take epsilon to be 1 and you look at the nonlinear evolution. And then what you need to estimate, so the technical estimate is that the L2 norm of this is bounded by G squared in L2. And for the cubic terms, you have a power to the 3. Yes, L2. Cube. Okay, so this you can prove. Okay, one way is to exploit the weights in the linearized equation. Because okay, when you linearize, you have all these weights here that are 1 over k1, 1 over k2, 1 over k3. And since I'm taking here, I can also write with this, a positive number, 1 plus omega k, you can have, say, with some cosine inequalities, you can bound some of the terms. But you can also control the L2 norm without using the weights. Since I also have a cutoff, it's not very difficult in this case. You can apply some TT star arguments. TT star, I'm just writing TT star, yeah, it's not very... right, okay. And then as long as you can control this norm of these terms, you can proceed with a fixed point argument to prove existence of the solution. So I don't know if I have time to say more on how the fixed point argument works, but yes.
So more or less, do we have 1 more minute? 1 more minute?
Okay, if I have 1 more minute, then let me say that. Let me state one more result then. So this is a joint work with Miguel Escobedo. Okay, so what we wanted to understand is, okay, so if you linearize around 1 over omega plus 1, then with L2 small initial data, it's you're stable around your equilibrium solutions. And it's not that the cutoff that I have plays a role in this. So the cutoff is only for technical reasons. It's not a crucial. So you expect this to hold in the whole space, this behavior. And it's important to linearize around equilibrium, which is of this form. So omega k plus mu, and mu is positive. Okay. Somehow, if you imagine all your equilibria, to be somehow, say, in a manifold, then as long as you have mu positive, you're in a safe part of the manifold. Whereas if you linearize around 1 over omega, then you're in some kind of edge and you have condensation happening. I don't know if this makes sense, but this is how I think of it. Yes. Yeah. So you want mu to be positive. Yeah, and also we assume that omega k is k squared. Okay, and a basic assumption here is that we work with a radial equation, so we assume that the solution is radial. In this case, the operator is very much like the Boltzmann equation, even the nonlinear, the Boltzmann operator. So it's you can take as your variable to be the dispersion relation omega, and you can write this as, okay, so you have the cross section to be the minimum of which is always bounded. And then you have F1, F2, the usual nonlinearity. Minus F2, F3. And where omega 3 is equal to omega 1 minus omega 2. Okay, and what we can show is that for on the whole space, you're L2 stable using the more or less the same machinery. We somehow remove the cutoff assumption, but we have one more assumption on the radial solutions. So, yeah. And the difficulty that arises here is, okay, because you don't have a cutoff, when you linearize, the difficulty is to control the nonlinearities again, okay? And when you linearize, you have a growing term in omega, because you have okay, so in front of your operator, you have a f infinity minus 1. So this is growing in omega, and this you cannot easily control. But you can do some dyadic decomposition on your integrals, and you can have you can still bound these terms, even though you're in the whole space. So somehow, if you try this dyadic decomposition that I haven't tried in my first two results, maybe it's also possible to remove the cutoff. But yeah, it's I don't know.
Yeah, maybe it's, yeah.
Yeah, I will stop here.
Is there any question? Yeah, so in the meantime, okay, can you, the last thing that you said, so in this new parameter,
Yes.
yeah, but I was a little bit lost at the beginning. I think I didn't get. So so it's still an equilibrium. It's a regularization. So yeah.
It's still the Rayleigh genes, but you take. Okay, so the Rayleigh genes is.
It's 1 over omega k, no?
Yeah. Okay. Let me
Without.
go to the end. Yeah. So the Rayleigh genes is 1 over omega, and then you have. Okay, this term for some b vector constant, and then some other constant here.
Omega is omega k. Omega of k.
Yes. Yes.
Yeah. Ah, yeah.
And then I call to mu. I call to mu the a.
Okay. Good. Any other question? Okay, so if not, let's thank now there is a coffee break, and then we start again at 4 p.m. The last talk.
I can close this forever.
It's maybe a commute.
prova a fare la condivisione dello schermo.
Presenta?
Sì, presenta. Fai condividi schermo. Fai... Sì, va bene, fai condividi schermo, metti full screen, quell'altro. Schermo intero. Ok. Consenti, devi consentirlo.
Zoom, no.
No, niente, devi fare Firefox.
Senti, finché non c'è quando registrare i contenuti sul tuo schermo.
Esce, riapre.
Ok, presenta faccio, no?
Sì, presenta di nuovo.
Condividi schermo. Schermo. Ah, aspetta, perché adesso c'è un'opzione in più. Schermo intero?
Sì. Benissimo. Aspetta un attimo.
Ora sei nella trasmissione. Ah, ecco.
Ecco, adesso tu condividi il tuo schermo, condividi, apri il PowerPoint.
Presenta faccio.
No, devi fare il PowerPoint. Se già condividi, questo non lo vedo, perché non lo vedo. Stai su un altro schermo.
Aspetta, fa così.
No, non lo vedo, aspetta perché non ti vedo. Aspetta un attimo. Aspetta, lo vedo, ecco. Ci sei, metti... aspetta, fermo. Sono io che sto troppo veloce che c'ho. Ecco qua. Fai full screen. Perfetto.
Ok.
Ci siamo riusciti.
Perfetto.
Perché,
aspetta, posso toglierlo un attimo?
Sì, come no, certo.
Ok, no, perché così metto la cosa di...
E poi tu parli da questo qua direttamente, capito? Ci apriamo il microfono di questo. Oppure,
okay. No, sì.
Oppure possiamo togliere il microfono. C'è il microfono. Adesso siamo online. Togliamo questo. Chi ti presenta? Roberta.
Io. Audio, it's already not. Okay. Okay, so this is the last speaker of this workshop, Andrea Scagliarini, who is a colleague here at the institute here in CNR. We talk about the right tail turbulence with density stratification.
Okay, thank you. Thanks to the organizers for organizing this very nice workshop and for inviting me. I mean, I'm really happy because I think I've learned quite a lot, and also because, as Roberto said in the first day, I mean, it's kind of unusual to be invited in your same institute. For me, it's the second time. It's the first one was the presentation speech. So, okay, I slightly changed the title with respect to what you can find in the program because, well, first of all, I think this one is a bit more inclusive of what I'm going to talk about, and which is not only this aspect of singular initial condition in temperature, but in general, it's about the relative of turbulence where you have, let's say, a complex background, both in terms of temperature and density. In fact, so the talk will be essentially divided into two parts. The first one is about is when the system can be considered Poussin-esque in some sense, but the temperature background is not the usual one studied in Rayleigh Taylor systems, and in a while I will explain what we mean by usual one. But in the second part, I really want to talk about, say, non-Poussin-esque systems, and so say non-Poussin-esque effect like stratification and incompressibility and so on. Okay, so what the Rayleigh Taylor, I decided to talk about the Rayleigh Taylor problem because, well, first of all, as I will show in a while, it has huge. Let's say there are not a lot of applications in geophysical flows, not only in physical flows, but it's very relevant in physical flows. And also, I mean, it is very interesting, and I think in certain aspects much less studied than other typical hydrodynamic instability like Rayleigh-Benard, for example. And it's very peculiar. It has some very particular features that make it interesting and beautiful in some sense. So what is the Rayleigh Taylor instability? It is the unstable instability occurring when you have a heavy fluid, or say a dense fluid, which is accelerated in some way against a lighter one. So a typical example is when basically you have a superposition of the two fluids under gravity, but it's not the only one. I mean, the acceleration can be realized in a number of ways, as we are going to see, for example, in thermonuclear explosions and this kind of thing. And like I said, it has many applications. I mean, I like it pretty much. I mean, I like clouds in general. I think that clouds are a very nice example of pattern formation in nature, and we saw this morning another picture of clouds, and it's very nice because I mean, in the clouds you can really read a huge number of hydrodynamic phenomena from Kelvin-Helmholtz instability, or waves, or even the Rayleigh Taylor. Typically, when you have this kind of clouds that have this sort of say down pointing modulated shape, like in the case of Mammatus clouds, Rayleigh Taylor instability is there. And also in this one, I brought this picture of this Asperitas cloud because I mean this is the newborn. It's the last the cloud that has been given a name, and it has been recently added to the International Cloud Atlas, and basically this kind of wave-like structures. Again, like I said, with the particularly holding down slash. Also, the famous downburst that recently in Italy we hear a lot. No, it's when you have this thunder, these storms where it's basically a burst of cold air, that impinges it so it's a really phenomenon. But like I said, it's not only in geophysical flows. For example, you see in supernova explosion, like here we have the Crab Nebula, each of the Crab Nebula. In fact, it is called nebula because the shape is that of is similar to that of a cloud, and is similar to that of a cloud because of the universality of the morphogenetic universality induced by Rayleigh Taylor turbulence, and also in some in the geodynamics and so on. Okay, so the Rayleigh Taylor is unstable. I put a question mark because since I met Roberta, all my confidences on hydrodynamic stability somehow crashed, so crumbled. So I'm pretty sure that still Rayleigh Taylor is always unstable. I mean, it's at least if you destabilize the interface, the fluid, in the linear regime, it grows, and with this growth rate, I mean, this is the viscous result, but the viscous result is a bit more cumbersome, but still is unstable. I mean, there are some stabilizing mechanisms. For example, if the two fluids, this is the case where the two fluids are miscible. If the two fluids are immiscible, so if you have a surface tension, then you have a negative term inside here, and so you have a critical wave number beyond which let's say the disturbances are stabilized. So so surface tension is a stabilizing mechanism. Also, if you have a wind, like a wind shear, but in that case it's more complicated. In that case, the instability is the setup is a Kelvin-Helmholtz instability, so it's a bit more complicated. Anyway, when these disturbances grow at a certain point, you see they kind of reach this plume shape, and that's where somehow you enter the nonlinear regime. Then this plumes stabilize, and then the nonlinear regime, of course, is a mess. And how messy it is, you can find here. So this is the simulation. Here you see, you start with this disturbance that I show you. This is the temperature field, hot, cold on top, and then hot in the bottom, and that's the corresponding velocity field. So you see, when you start to have this growth of at a large scale, somehow the interest is to show to see how this mixing layer has its called growth, no? And how do the profile? We see what I was saying. It's pretty complicated. The interesting thing is, you see, this is really a turbulent system, but unlike standard turbulence, like for example, really Bernard turbulence or homogeneous turbulence, I mean, this is non-isotropic, no? Especially at the beginning, because you have the turbulent system. The system itself is evolving, right? It's growing, so the large scale is growing. The Reynolds number is growing. So it is non-observable, it's non-homogeneous, and most of all, it's non-stationary. So the turbulence, the turbulence scales grow, in time. So in this talk, I will focus only on the large scale evolution. That was what I decided, but I mean, probably I should have talked a bit more also about the roughness of the velocity field at small scale. But anyway, so okay, so these are what I already told you. This is how the system is initialized in general in the standard radial case. Standard radial case, you have a constant. You have basically a stepwise, a step function, at the beginning. So you have a hot temperature at the bottom or the top, but they are uniform in these two subvolumes. And the equation are the Rayleigh-Business equation plus the vector inclusion for the temperature equation. So yeah, this is the condition. The control parameter is this output number, which is basically a non-dimensional quantification of this the forces, so say the temperature difference. Okay, so the sketch here is 2D, but the simulation are 3D. This is a snapshot of the simulation, at least for this part. They are 3D. Okay, I don't want to enter on the numerical details, but anyway, it is absorbed by pseudospectral code. And so, like I said, I mean, the interest typically is in studying how this layer, this mixing layer, grows in time, and how the temperature profile, evolves in time. You start to know the profile here means, the average along the, let's say, the gravity normal direction from the temperature field. So you start as I show you, that we do the step function, things like that, and then of course here you start to mix, and so you start to develop this apparently linear, but it's not linear profile. Okay, one of the well-established law or observation in Taylor is that this mixing layer will grow quadratically in time. And
this one is just a cut.
This is a
cut. The 3D
no.
Or just 2D.
Okay, well, I'm missing things. So this is 2D.
Okay.
But just for visualization.
Yeah, but is there a difference between 2D and 3D in this case?
Okay, no. So from the point of view of evolutions of large-scale quantities, like the mixing layer width or the temperature profile, there are no. There are yes, and particularly important when you look at the small scale. So, for example, at the analysis and probability of the velocity field, of the temperature field, all the singularity indices are different, because in 2D you don't have direct cascade, and in 3D you have direct cascade. So, yeah, but from the point of view of, let's say, the large scales, essentially the phenomenology is the same. That's why I'm mixing things. But anyway, yeah, these simulations are.
Okay, I'm just understanding.
But the cut.
This one is.
Yeah. No, I mean it's a good question, because you will see later that there are differences, because here, because it's 2D, you start to observe the formation of these big vortices, which is typical, let's say, 2D feature, so to say. Okay, so this is just a sort of way to compute the mixing layer width. That can be computed either as with the cutoff or criterion or with the neutral criterion. We observe that indeed it grows quadratically. But why it grows quadratically? Well, there are some phenomenological arguments, and that go in this sense. So basically, from my associate, you know that the acceleration goes essentially this force goes by as the beta, which is the thermal expansion coefficient, the gravity times the temperature difference, and from a dimensional estimate, basically the acceleration can be written as a characteristic velocity over a characteristic large-scale turbulent time, which in turn depends on, is basically a ratio of this length, because the large scale, like I said, this is an evolving parameter, which is growing in time, divided by the velocity. So essentially, this is the an estimate for an alternative estimate for the acceleration, and if you put things together, you end up with this equation that can be integrated, of course, and you have this expression where h0 is sort of initial height, and in fact, I mean, there is a linear part, but after a certain time, the quadratic part dominates, and in fact, the growth is quadratic, and okay, this alpha parameter is a sort of phenomenological parameter. It's a proportionality constant, which for many years was not, I mean, was basically the holy grail of Taylor. I mean, everybody was just studying, let's say, measuring this thing and how it depends on a number of parameters without really understanding what was its physical meaning. But we're going to check it in later on. In fact, there was also an alpha-group collaboration that they made. Yes?
No, this is a very nice question, since I'm not a programmer. But how much of this extends the case of the indicted fluid?
Sorry?
How much of this extends the case of the indicted fluid?
Well,
you had the analysis, right?
So somehow here, this estimate is, you don't have viscosity there. The noise implicit. It's just no. It's basically it's not it's this one. No, so it's just the acceleration equals the force. Right? Because somehow we know at the large scale you don't care about let's say any viscous mechanism. Then of course here, I mean, this is
So it holds for formally holds for.
It's formal. Yes. And so there is this alpha rotation. They make a collaboration to measure this alpha in many ways. You see, I mean, all these people come from places like Lawrence, Livermore, Laboratory, Atomic Weapons Establishment, Sandia, Asian Laboratories, which already tells you something about what was the specificity of Rayleigh Taylor for many years. In fact, most of these things are classified, so I'm not going to enter particular details, but okay. So the other large-scale point is that one might want to be interested in is the evolution of the mean profile. So the mean profile is essentially where you will see this overline everywhere, and so this overline is basically an average over planes or lines in the case normal to the gravity. And that's what one would like to understand, no? So how this profile, which starts with the step, evolved in time. No? As time goes by, it starts to be more and more bended because the layer is mixing. And then how you see it's never constant, right? So the system is always somehow non-isotropic in some sense, no? And non-homogeneous. There is a large scale which matters. So how can be done? How can this be done? So if you start with the field equation, the advection field equation for the temperature field, and you write the equation for the profile. So you basically just do the integral to this, to the equation. Consider that in the system is periodic, so in the other two directions, so in x and y. Which eventually leads you to this equation, which of course, I mean, somehow you didn't find anything, no, because it's not closed with respect to the temperature profile. You have this thing, which is not the mean for the heat flux, right? So say, okay, then let's try to write the equation for the heat flux, which is something like that. But then you have another flux. I mean, this and so on and so forth. I mean, this is the famous closure problem too, or any nonlinear field theory, which is, let's say, nuclear field.
So you start now is bring the average with the x and y here.
Yes. Okay. Yeah. And okay, it was a standard procedure which is relatively old. The turbulence theory is to close the equation. Okay, we have to find a model for for this thing, for example. Now you start with this equation for the profile, you have to find a model for the flux, for the heat flux, and the turbulent heat flux. And okay, first, the easiest attempt, one can imagine, is the diffusion approach. We base back to Taylor and Richardson. And which basically amounts to say, okay, let's say that this heat flux is proportional to the gradient of the mean profile itself via an effective function, which is sort of effective diffusivity. Why is it called an effective diffusivity? Let's say by analogy to molecular diffusion, right? So molecular diffusion, so the diffusion at the molecular level, or like viscosity or whatever, is basically originates from collisions between particles that make some, and then in fact it is proportional to the mean free path and the root mean square velocity. So in this case, the idea is that a parcel of fluid is affected by eddies. That's why it's called eddy diffusion. And then how should look like this effective diffusivity? Well, as the product of a characteristic velocity and scale. Large velocity, large scale. And what are the characteristic velocity and scale in Rayleigh Taylor? Well, the mixing layer length, of course, and its derivative, which again, by the phenomenological argument that I gave before, essentially goes as this combination of parameter here, or be some proportionality constant, some phenomenological parameter that has to be, sort of input. And okay, if you plug this then inside the equation, you end up with, you can see that you get this equation, which is now closed for the temperature profile, and you can solve it. You can redefine the time by for the initial time with this initial condition, or with the step initial condition, essentially. You can solve it, and the solution is this error function. So it's a set similar solution. The solution is the error function, and the scale factor obviously is basically the mixing length, or say half of the mixing length, if you want. And okay, so if you write now, I produce this non-dimensional profile, which will be useful later. It's basically the minus the mean temperature profile divided by the temperature difference, and you see it goes quite well. So the dots here are the results of the simulation, and this dotted line is the result. Now, if I didn't put this here, you would believe that the thing worked very well. But I zoomed up on purpose, not because of big big, and said, okay, well, it goes well, but not perfectly. And the reason is that, so you see here, this at the effective diffusivity is homogeneous. It doesn't depend on Z. But let's say the characteristic velocity instead does depend on Z, because, like I said, in the center of the mixing layer, with respect to the edges of the mixing layer, the intensity of turbulence is not the same. And so one can make things a bit better and use the approach, the problem, the closure using the Brandel's mixing length. The idea is more or less the same, but it takes into account the fact that that you can have a non-homogeneous background, and so you can write this effective diffusivity as characteristic squared length times the derivative of the space derivative of the velocity. Now again, the velocity is given essentially by the temperature times times time. The length is the characteristic length is the mixing length, so the mixing layer of width. And so if you put things together, you end up with this equation now, which is similar to the other one, but it's not linear. In fact, if you introduce this, you introduce this scale time in this way, and this variable phi like this, the equation leads to this one, which is a nonlinear equation that is, however, quite well known. I mean, I didn't know it before, so if you don't know it, don't feel sorry. It's basically it's called in the literature, at least in the physics literature, as a focus moving equation with the index m equal 2, and it has a solution, a similarity solution, which is the Barenblatt Kompanetz-Zeldovich solution. And you see now, okay, this is the same figure as before, but here now you have also the solid black line, which is it's not a function, but is this similarity solution, and you can see that indeed things go better. Okay, so this is somehow sort of history, not very old, but anyway. But in any case, is in the standard really configuration where you have the temperature that has this jump at the beginning, but it is homogeneous then in the two subvolumes. Anyway, the atmospheric boundary layer is a complex animal. No? In the boundary layer, you have many processes going around, and you have shear, you have so on and so forth. So if you measure the temperature profile, you discover that it has some power law in general behavior anyway. It is not so. It's not homogeneous at all. No, for example, the Moin-Nobukov a singularity theory, which deals with that. It has in fact a power law, which is also in general with the non-integer exponent. So here came the idea then to study this problem where the initial condition is not anymore just the step function, but it has some some power law. Right? The point is that this is not this power law in general can be positive or negative, but it's taken as smaller than 1. The point is that it is not only the initial condition, because the temperature is what forces the equation, forces the initial equation. So the fluid feels constantly this rough background, this singular background. So the idea was to say, okay, let's see if the argument, for works as well, for example, in terms of the evolution of the mixing layer length and mixing layer width. So the argument, okay, the technology argument is the same. Only thing is that now you see T is not constant. It's not just the temperature difference, but it's the temperature difference at the scale of the mixing layer width, which depends on which is a function of h. So it's a power law of h. Anyway, so you can integrate this, and you see that still goes as a power law, but of course with another exponent that depends on the singularity exponent of this temperature profile. The interesting thing is that, okay, so this is the solution in principle. Formally, just it's just a manipulation of the exponent. You can rewrite that this way, so you can take out the quadratic term, and then you have a time-dependent output number. Now, why do we? This is just done in order to see that you have basically a time-dependent output number, which somehow tells you that the system behaves, even if it's the temperature, it's non-homogeneous. The system behaves similarly to time-dependent acceleration, and to systems where time-dependent acceleration, there are many systems of this type, and in particular, it is the case of inertial confinement fusion that is tells you why there are these people at Livermore and the atomic, whatever, because in fact, inertial confinement fusion is another example where the Galileo plays a role. Anyway, going back to the result, in fact, so this is the mixing layer with evolution, a function of time, for 3 cases. The C equal to 0, which is the standard one, and then one positive and negative C. As you can see, the positive one, which is somehow less accelerated at the beginning, because initially, the temperature difference is 0. It takes more to reach the similar region, but then all the 3 tend to this exponent, this power law with exponent, which agrees with the phenomenological formula. But the 3 are different, of course. It depends on C. So now the question is there a way though to recover this Taylor universality? So in which sense these systems are similar to each other? Well, so the idea is the following. So one can write a conservation equation, global conservation equation. So now the brackets have the total space average. And the conservation equation is this one. It basically tells you that the consumption of the loss, the potential energy loss goes into kinetic energy plus dissipation. And so you can write you can define a quantity, which is the ratio minus the ratio of the kinetic energy to the potential energy. So it's a sort of efficiency of conversion of potential energy to kinetic energy. It's a sort of efficiency of the mixing process. And again, if you estimate the energy energy is electricity velocity square for each dot square and the potential energy in this way, this should be T. See that the ratio is this guy here. That if you recall the similarity equation that I gave earlier, I think this is basically the famous alpha. So this alpha, in fact, as a physical interpretation, is this sort of efficiency of the mixing process. And okay, interestingly enough, this if you look at instead of looking at the growth of the mixing layer, you look at this efficiency in time, you see that somehow you recover the new set. So this is independent of C. The three curves. So the green one doesn't look very well because it's much faster. But anyway, the other two, this is again it's equal to 0 minus something plus something. Go one on top of the other in the self-similar growth. So there is still a self-similar observable that is universal in terms of the even on this temperature non-homogeneous background. Okay, so this is concerning the temperature profile. Notice we look at the temperature mean profile. We will let the same now. So the procedure is the same. Only thing is that we have to find another ansatz for the heat flux because, and basically the difference is in this extra term, which is added to ensure that the heat flux vanishes outside the mixing layer. Because now the temperature is non-zero even in the mixing layer, but you don't have a heat flux there. Okay, the equation for a homogeneous diffusivity is this. So it's this one. Now it's close with respect to the mean temperature profile. The closure is the same. It's an homogeneous closure, so it's the product of a characteristic length and characteristic velocity. Of course, the time dependence is different because it depends on C. But the interesting thing is that one can find this in a similar way, similar solution, sub-similar solution also in this case, which is given here. So it has this term which is reminiscent of the background profile times sub-similar function, which is given by this integral here. And of course, you see if you plug C equal to 0, right, this disappears and you recover the error function solution that I gave you before. And so if you look at how it looks with respect to the numerical data, it looks pretty nice. So these are the three cases, 0 singularity index, positive and negative. The dots, the different colors correspond to different times. So if you plot the things appropriately, so T divided by the scaling factor and with respect to the similarity variable, you see that basically all the points at different times collapse onto the same self-similar shape, which is the one given by the equation as I gave you before, whose expression is here represented in the solid line. How much is that? Good. So okay, so good. So far so good. This somehow closes this first part. So so we show that the process of the growth of in general the radial evolution in terms of growth of the mixing layer width, the evolution of temperature mean profile for radiator tubes on a rough temperature background goes similar to the standard case, but with in exponents and with the shape of the temperature profile, which of course depend on the singularity index. On the other hand, the universality can be recovered in terms of this variable, which we call the efficiency of conversion of potential into kinetic energy. Okay, so far so good, but like I said, now the actual, let's say, geophysical flows are pretty complex, and in general, it's not only that you have temperature. I mean, you can.
so until now, it doesn't make sense. So K of T, K is only a function of T. There's no Z inside.
Okay, so here, yes. But I showed also a case where it depends, you said on Z.
K, yeah.
Yeah, yes. So you can do both things, right? So here, yes, for simplicity, because you already have the complication of the temperature profile is only it's a homogeneous case which depends on T. But here, in this other case, yeah, this one was dependent on Z as well. And in fact, you see, the point is, of course, if you make you get a nonlinear diffusion here. No, you have, in the other case, you can always recast the equation into the heat equation.
Yeah.
In this case, you can. Fortunately, you can recast it in this thing, which is nonlinear but known somehow. And but yes, and the difference. I mean, you have a difference. You know, so yeah, the difference looks slight, and it is, but it's because somehow you have a finite side effect. And if you can let the mixing length layer become longer and longer, then you start to dissolve more of this region where the difference between the homogeneous and the space dependent had the diffusivity matter. So. So you know, geological flows are in general stratified, compressible. No? You can assume that it's an ideal gas. I mean, it's compressibility matters, and also it's not only the temperature that varies, but the pressure in the atmosphere is stratified, not because you have a static equilibrium. And so this is what I'd like to address now. So in the case where you get rid somehow of the Boussinesq approximation, then you will use it in some sense, but and you consider the whole, I mean the full equations. So Navier-Stokes plus the energy equation for an ideal gas, which are these equations, which are nasty. You see, and in particular, look at the energy equations, the equation for the temperature. You have the compression term, the viscous heating, although the viscous heating, in high Reynolds and especially in 2D is basically irrelevant, but and so anyway, even in this system, let me first say that the numerical simulation solved the full set of equations. The numerical simulation now is a different one. Now it's 2D, and it's a thermal Boltzmann error for multi compressible flows. But let me say that it is possible to perform a sort of Boussinesq limit for this weakly compressible case for this ideal gas. Basically, writing the hydrodynamic variables, pressure, density, also temperature, as the sum of the mean part, the profile, and fluctuations, and then in the situation where the globe, the density difference is evaluated globally somehow with respect to the mean are small, you can end up, and of course the P0 and the P naught and rho naught, so the density profile and the pressure profile are related, not related by the hydrostatic equation. You can boil down this very complex system to this one, which is much less complex. It's basically Boussinesq, but you have the emergence of this term here, which is as we see is very important. It's basically it is a term proportional to the velocity in the z direction times a coefficient which is this guy here. It's the ratio between the acceleration of gravity and the heat capacity, and this is called the adiabatic gradient. I will explain later in why it's called so. So okay, what is the so now the initial mission is different. It's a step for the temperature. We don't want to mix the two things because it's so the temperature now is taken as the usual relative step, but the density is not constant. Now the density has to fulfill the hydrostatic condition, and since it's an ideal gas, it basically depends on the by the equation of state, depends on on the local temperature. No? So it has this expression, exponential expression, decay in both sub-volumes, but depending on, of course, the different temperature. No? The two, basically the two prefactors are fixed by the mechanical equilibrium, by the fact that the pressure has to be the same at the interface. Okay, so let's see what is the effect of this adiabatic gradient. So this is the same movie that you saw before, and this is, which was a weakly stratified one, or unstratified, let's say, and this is the strongly stratified one. Let's see what happens. So the beginning is pretty much the same, and then let me speed up a bit. Okay, you see, while the weakly stratified case, as you saw before, goes indefinitely up to reaching to filling the whole volume, in the strongly stratified case, the mixing layer growth stops, no? And then it goes on as essentially a confined turbulent layer, which is this is what I meant before. It's really beautiful because it's really good looking in that sense. So it really reminds like the Van Gogh's Starry Night, and the palette, in fact, is not shaded; it is chosen in that. And so you see that now this is 2D, and you can recognize it also at the naked eye by the formation of this, vortex structure, like the Jupiter atmosphere or things like that. So sometimes you have these paths which are dynamically very important, but essentially is confined.
But the adiabatic gradient is a number, no?
It's a number, yes. It's a constant.
But it can be more or less the number which is in front of you.
It is related, yes.
Yeah.
Yes.
So it's a kind of.
It is related. Yeah.
So I can say it's a kind of effect of stratification.
Yes, it's the stratification. It's exactly. It's the stratification that does this, and it does this. Okay, so this is just okay. You could have inferred it easily. If you now look at the mixing layer width, in the weakly stratified case it grows as before. The strongest stratified case it grows, and then you reach the plateau, and it stays there. And no, it's the stratification that does this. In fact, because you see, essentially, what forces the temperature, what forces the velocity is the temperature. No, but in the temperature you have this combination of curves. Now, when the temperature gradient reaches the adiabatic gradient, I mean, the forcing on the temperature vanishes, right? Because you have UZ and UZ, and so this is what happened to the velocity, to the temperature profile. No, so this temperature profile is the temperature, it bends as it did before, but then it stops. And where does it stop? It stops at the adiabatic gradient. No? Or if you want, the mixing layer length reaches this adiabatic length. No? But look at here. You see, it's not only. You see that the shape is pretty strange, right? Because you have this not only the fact that it stops, so that it reaches this adiabatic gradient, but also it develops these bumps, these overshooting regions. And the origin of the overshooting region is this. You see, like in this cartoon here, is this puffing, this turbulent burst of higher dense fluid which are pushed in the higher atmosphere, but then by gravity tend to take them down again. See, this essentially this is what happens. These puffs which are responsible of these overshooting regions. And and these overshooting regions are not a bit of pain in the neck if you want to model, because you see now in the correspondence of the overshoot of the mean temperature profile, the heat flux becomes negative. And anyway, both the mean temperature profile and the heat flux are non-monotonous. And so the idea of closing, if you want to look at the equation for mean profile, if you want to close it at this first level, so at the level of the heat flux, I mean, it's hopeless somehow, right? Because you have this region. So any first order closure may fail. That is the idea. And so we say, okay, what can we do? Let's go in order to the second order. So we keep the equation for the mean profile equation for the temperature. We keep the mean profile equation for the temperature exact, right? So we don't close the heat flux, and then we have to write the equation at the second order. So the equation for the heat flux, the turbulent flux, the kinetic energy, and the temperature fluctuations, which of course, as we have seen at the beginning, involve third order, quantity, and then now you have to close the third order quantity. And for the third order quantities, so let's say the fluxes of the fluctuations of the fluxes of the flux, we use this again, a local closure. So let's say yes, so according to a homogeneous eddy diffusivity ansatz, right? So depending only on time, to make things to keep things simpler. So the flux of the fluctuation will be proportional to minus the gradient of the fluctuation profile. The velocity will be proportional to the flux of here that should be u squared is proportional to the gradient of the u squared profile, and so on. And so yeah, again, the equation, the closure is taken as a homogeneous one. So all diffusivity is essentially proportional to the mixing layer length and mixing layer width and its time derivatives. So that are sort of again characteristic velocity and length. And but you have also to close the to write an expression for the dissipation. And which is basically each dissipation is essentially the corresponding fluctuation profile divided by characteristic time. The characteristic time is taken as the characteristic length h divided by the mean square velocity profile. So okay, then all these numbers in theta and u, and because you have also the cross term and the b are say fitting parameter, phenomenological parameter. So there are many of them. There are 6. I had a colleague who used to say, with 2 parameters I can fit you an elephant. With 3 I can fit you even my mother. So imagine with 6. But okay. So the first 3 are, you can get all of them from first guess from the simulations. And you see that the first 3 are relatively robust, because it's simple. It's just what you can do. It's the diffusivity is homogeneous, and they are all more or less order 1. In fact, you can take this first guess and keep them constant. So these are, say, 1 or only 0.8, but we fix them. Then you have this. You are left with these 3, but one is the one in front of the energy dissipation, which fortunately is irrelevant in 2D because you don't have a direct cascade. So essentially, the only critical one are these 2. And so, okay, we can fit the elephant, but not the mother, because we have only 2. Anyway, so yeah, you can check, say how robust they are. And so here, for example, here we have the results from the model. Okay, so you can just say one detail. Okay, this is now you have this. This is a system of differential which can be solved with some standard method, implicit in time, whatever. So it has to be solved numerically. That's what I would say. So we have 3 cases. In particular, one is the weakly stratified case, where essentially the system size is comparable with or smaller than the adiabatic length. And the other 2 instead are such that the adiabatic length is larger, smaller than the system size, so the system source. And these are the corresponding length, width, sorry. And so here we have, here basically we have tested the model fixing one of the 2 parameter and varying the other, and the shape, the color there is basically the error bar. And here we have done the opposite. Anyway, in both cases, the model seems to be pretty robust. And this is so the solid line is the best of so this is to test the to select somehow the parameter, this is the parameter range. And then we looked at what we were interested in, the width, but also the mean profiles. The mean profiles are very well captured, of course, in the width classification, but that was easy, even Crandall and do it. But also the strong stabilization case. You see, now we get the overshoot. We get the overshooting region, which is quite nice. And actually here this is the derivative of the temperature profile, and on top of the second order closure, which is the solid line, I plot this one, the smooth crosses. This is the rectangle. So this is the Barenblatt-Serdovich solution. So you see in the bulk, in the very bulk, let's say they kind of perform the same, but then as compared to the dots, which are the numerical data. Anyway, that's a weakly stratified case. So the weakly stratified case, in fact, also the Crandall case, so the Barenblatt-Serdovich solution works. So then, of course, once you have the expressions, for the velocity, the mean profile, the temperature mean profile, and the heat flux, then you can do a sort of reverse engineer. You can do a sort of a posteriori check that your closure was reasonable. So you can plot the heat flux versus you do a scatter plot of the heat flux versus the profile, the mean heat flux versus the mean temperature profile, and see from the simulations, from the numerical data, and see how they go. And so you see, again, you have the weakly stratified case there and the strongly stratified case here. And the solid lines are the closure, the dots with this very huge error bars in both directions are the numerical data. But con grano salis, so saying with a grain of salt, the posteriori check is quite good, right? You see the solid line kind of, in fact, interpolate well the reasonable the numerical data. Interestingly, let me say, you see in the weak stratified case, there is a region, relatively extended region where it seems to go linearly. So, which is somehow the Crandall assumption. So, in the weak stratified case, Crandall assumption still works better, but works okay. But in the strongly stratified case, of course, there's no way. But with the second order closure, you can capture even the region where the heat flux becomes negative. And okay, this is basically ends up. So we've shown that when you have compressible atmosphere, so to say, so a huge compressible atmosphere, and you have stratification, the density variation, even the large scale dynamics of of turbulence is strongly different from the non-stratified case, because you have this phenomenon of the arrest of the growth of the mixing layer width, and that we could reproduce, whose dynamics in terms of both the time dependence of the width and the velocity profile and heat flux profile, we could reproduce relatively quite well, proposing this second order, so this closure of the equations, statistical closure of the equations, which is done in the spirit of keeping exact equation of the mean profile. So the first order two close quantities in the second order. And yeah, basically, I think that's it. I could just mention my collaborators, so Luca Biferale, Andrea, from the University of Rome, Vergata, Guido Boffetta from the University of Turin, Alexei Manibayev from the Institute of Pure and Applied Mathematics of Rio de Janeiro, and Lele Trupiccione, who sadly passed away a couple of years ago, and and of course the audience for the attention.
Thank you. Question. So can you just coming back to the model explain a little bit? So this weekly complexity in the model, where you see comment a little bit of this the weak complexity.
You mean the equations or the
weak complexity?
Okay.
Yeah, the equation.
Yeah. Yeah. So you mean how to go from here to here?
No, just because, so the weak complexity, you mean this parameter is...
Okay, what is the weak compressibility?
Yeah,
the weak compressibility is that you don't have strong density variation in the system. By strong density variation, you mean the maximum minus the minimum of the density variation with respect to the mean should be much smaller than 1. In fact, say this is the condition is slightly different. I mean, eventually it boils down to this one. The condition is that the typical stratification lengths, or the Cartesian lengths, which are defined as basically the mean divided by the derivative, are say large.
Yeah. But the actual field is divergence free.
In the end, yes. Okay. Yes. Okay. So the full equations are not, and the full equations are compressible. Yeah. But if you do the calculation, in the end, yes, the velocity is field is the velocity is divergence free. Not is
I mean, when you pass the Business limit,
yes,
the density becomes almost constant.
Basically,
this is recover.
Exactly. I mean, this is just a way to show, to single out where all the stratification thing comes from, which is the adiabatic gradient, so to say. So this is essentially, Bussinet, you see the density somehow disappear. You have the divergence free, you have the Bussinet curve, the temperature fluctuations, but you have this term. Which is
it's Business around the stratification.
Notice that I mean this is done to do the theory, for the analytics and so on, but the simulations solve those equations. The point is that in the end, you are weakly compressible, and so you have this limit because somehow if you make the system, so if the output number is small, if these differences are small, the gravity is not too strong, and you go down. I mean, you cannot do very too much compressive anyhow, with this method, with the displacement method.
Another question. Can you explain a little bit the Brandt assumption?
Yes. So, the Brandt assumption is essentially the same as in the homogeneous case, but you see, it's because it's basically the idea is that if you can have the velocity, the characteristic velocity itself is not homogeneous, right? And so the idea is that is that if you have this L, this characteristic length, which is called the mixing length, is considered, assumed as a sort of persistence length within which say a certain parcel of Friedman chains is its coherence in a background which depends on Z. So instead of taking the velocity times a scale, you take this scale square times the derivative of those to extend to a situation where you have, let's say, non-homogeneity, the standard the approach. It was when you have a profile, so you have an underline, you know, for example, it's done also, you can do also for the temperature, for example. And,
Yeah. Yeah, so you mean,
Yeah.
you provide.
Yeah.
Okay, so if not, let's thank Andrea.
Thanks.
And thanks everyone for coming. It was a nice event. Yeah, that's all. It's all for today.
Yeah, thank you to the organizer.
Sì,